So this PPT file is basically the same PPT file I used for the standard 3 hours training for FluidFlow. So it's been 2 years we are associated with Flight Software. So Flight Software is the developer of FluidFlow software, and in last 2 years I have trained more than 1,500 participants in FluidFlow, and for them I use this PPT file. So many things will not be applicable for us. So CEPL, so that marketing I can skip for now. Yes, so FluidFlow overview. So as I said, Flight Software is the developer, and this is quite old company. In 1984 they started. At present they have got more than the clients, customers in more than 68 countries. I personally used several hydraulic simulators. Okay, so PipeNet is there, Bentley WaterGens, Bentley Hammer, and I found FluidFlow is the most comprehensive. It is easy to learn and easy to analyze. Okay, so both are very important, and FluidFlow has done very good thing in those in both the departments, okay, learning and as well as analysis part. It has got intelligent and easy to use graphical interface so that you will have very good word file, simulation file, and it follows the international standards like ISO and API. So if you have any control valve, so it will use what standard? Chirag?
IIC, control IICS ANSI IIC 75.01.01.
Very good. And if it does say orifice sizing, then what standard it will use?
ISO 5167-2.
Very good. Right, it has got total 5 modules: fluid for liquid, then gas, two-phase, non-Newtonian and slurry, and then scripting. Liquid means, as the name suggests, if you have any cooling water system or fire water system network sizing, then you will use this module, fluid flow liquid. If it is a compressible compressed gas or compressed air supply system, then you will use fluid flow gas module. If you have two-phase system, like say oil coming out from the well, it has got oil and gas. So for doing the pressure of calculation, you can use fluid flow two-phase module. If your fluid is say paste, non-Newtonian, or if it is slurry, like say sand and water, so those kind of hydraulic simulation that you can do using fluid flow, non-Newtonian and slurry module. If you want to know how much time it will take to fill the tank or empty out the tank, so such simple dynamic analysis can be done using scripting module, right? So before we proceed, I need to ask, what is the difference between process simulator and hydraulic simulator? Yes, Tarun, what do you think? Process simulator and hydraulic simulator?
Sir, I think hydraulic simulators is only limited to the calculation which is associated with piping network or fluid flow, two-phase or multi-phase. But process simulator, they have no limit. They can go up to any unit operation and unit process they can simulate.
Correct. So if I want to do the distillation column sizing, I cannot use hydraulic simulator. That is only for pressure of calculation, right? So if you have some say cooling water supply system, this network simulation to be done. So can you use HYSYS for that? The system is, your tank is there, cooling water tank is there, then pump, cooling water supply pumps, and that header goes to say different heat exchangers all over the plant, right? And the temperature will get increase of cooling water, and this cooling water will get connected in cooling water return header, and it will go back to the cooling tower top. In cooling tower, the temperature drop will be there from say 40 degrees C to 30 degrees C for the cooling water, and again the same cycle will get continued, right? Capabilities, as I said, it can do simulation for liquid, gas, two-phase, slurry, non-Newtonian. Good thing about this software is it has got 1250 fluids data already available, like say methane, ethane, okay, water. So all this common fluids data is available. Its competitors has less than 10 fluids data available. So you need to go to Google and find out for given temperature, pressure, okay, what is the vapor pressure, what is the density, viscosity, and it has a lot of equipment also, shell and heat exchanger, okay, PHE, backbed. So if you want to know what is the delta P across, say, shell and heat exchanger, if our fluid is going through the tube side of shell and heat exchanger, so depending upon the tube ID, tube length, number of tube passes, it will calculate the pressure drop. Okay, in other software, you need to give a reference value, like say if the flow rate is 100 meter cube per hour, then as per vendor datasheet, the delta V would be say 0.5 bar. If the flow rate increases, delta V will also increase. So that kind of manipulation will be there in other softwares. But here, the accurate number you will get. Then layouts can be seen in orthogonal or isometric view. We can do the heat calculations also. Okay. So this again a unique feature of this software. For other software, you don't really get what is the temperature increase or temperature drop. Right? Let's say steam pipe is there, say 100 meter. So with insulation, what is the temperature or heat loss to the ambient, and with insulation? So we can get a better idea what should be the economic insulation thickness, right? Then it also helps us to find out the mistake that we have done in the model, right? It will give warning that here for this equipment you have done something wrong. This is extremely useful feature, right? If your model is very big and you run into some trouble, other software will not help you pinpoint that mistake. FluidFlow will help you. Then graphs can be generated in for various properties of the equipment, like pump is there, so pump data can be generated. Reports can be generated in different formats. You can import or export data from Excel format. Let's say it's only one tank, one pipe, and another tank, right? So you can just click on the pipe and type the length, the diameter, etc. But just imagine that you've got hundreds of lines, hundreds of tanks, right? Hundreds of fittings. So that data, if you type manually, like click on one pipe, give the data, then go to the next pipe, it takes a lot of man hours spent for that activity. So there is one feature in FluidFlow that you can model the you can prepare the model, then the blank data you can export in Excel file, right? From Excel file, you can from your input table, you can just copy that data and put it in this exported Excel file, and you can import that file back to FluidFlow, so that you don't have to type it, right? So it saves a lot of man hours. In one of our projects, we used FluidFlow. It has got around 900 something pipes. We saved a lot of man hours, okay, using this particular application in FluidFlow. Then it has got standalone license, it has got network license, right? It has got perpetual option, purchasing option, or you can go for yearly lease. Means every year you need to pay to maintain the license. The major clients include Worley, BASF, Eco Solution, then Shell is there, Sabic uses, even NASA uses this software. In India, we have been able to sell this to Tata Steel in Jharia, Jharkhand, in India, and in Mitsubishi Hitachi in Bangalore, again in India. All right, so enough theory. Now let us do the practical stuff. Let us start with a simple problem. Now in this problem statement, you have these two tanks, right? So one is overhead tank, which is having elevation 2 meters, and the other tank is at the ground level, which is 0 meter elevation. So what is the elevation difference? 2 minus 0, 2 meters. So if I connect these two tanks with these two pipes, like one is horizontal pipe, 10 meter 2 inch, Okay, and there is a vertical pipe, again 10 meter and 2-inch nominal size. These two pipes are connected by a bend. You can see the 90-degree bend is there, right? So if we connect this system like this, will there be a flow? Right, flow will be there, right?
Yes.
Okay, and this potential energy, what is the formula for that? Potential energy?
MGH.
MGH.
Rho MGH.
Okay, there is at least one guy who would say H rho G. It is MGH. Potential energy is MGH. That will be converted into what? Kinetic energy.
Kinetic energy.
Okay, what is the formula?
1/2 rho is.
Okay, half mv square.
Yes.
So that mm get cancelled. So it becomes GH is equal to half v square. Right. So you can
That's
calculate the
Ben-
velocity. Now you know.
Bernoulli's equation.
Yes, you know the nominal size, so you can find out the ID. So you can know the meter square cross section area of the pipe. You already calculate the velocity. So meter per second into meter square. So you get meter cube per second. So from that you can calculate meter cube per hour. Right. So that's how you get the flow rate. But big assumption that there is no friction, but there is friction. Right. So that H rho G, MGH and that half mv square. So that you cannot use it to find out the flow rate. Right. So that's why we need to use different equations that we'll see. Now, first thing you need to do, please open the fluid flow, this window, new file. So this one also we are going to do this together. Okay, hands-on training. So let me first explain the different items available on this file. So there is this horizontal model palette, right? It has got pipes and boundaries till heat exchanger. So if I click on the pipe and hover over here down, please look at my screen. So there is steel pipe. If I move cursor a little ahead, it says stainless steel pipe, then ductile iron, cast iron. So different types of pipes are available. Even plastic pipe is there, and hose is also available. If I click on boundary, if I click on boundaries, then I got this known or assigned pressure. Meaning, boundary means you remember in the PFD and PNID, we had got this flags. Okay, inlet to our system and outlet. Okay, exit from our system. So that was the boundary, the start and the end point. Now in this case, what is the start point? This first tank, right? And what is the end point? This point, this tank number 2. Do we know the pressure of 1 and 2? This is ambient storage tank. So we know the pressure, it is 1 atmosphere, correct? So when we have the idea about the pressure, then we'll go for the first. In the boundaries, we'll go for known or assigned pressure. See that?
Yes.
In some cases, we don't know the pressure, but we know the flow rate. Like we know that the 20 meter cube per hour water is entering our system. So that time we would go ahead with this. So then pressure will be back calculated. Then there is vessel, there is open pipe, there is the sprinkler. Okay, there are other options also. The third one is the junction. So in this problem, okay, so this is a bend, right? So we can go for this bend. Meaning if I select this, it will calculate some pressure drop. If I use meter bend, it will calculate some pressure drop. Okay, if there is some other fitting like T, symmetric Y or cross junction. So it will do some delta P calculation. But if I don't want pressure drop to be calculated for that connector, then I will go ahead with this connector with no resistance, right? In our problem, we are going to go ahead with the bend, this one. Okay, the next is boosters. Booster means if I hover over here, the first one, it says centrifugal pump, rotating PD pump, fan or compressor, then PD pump or compressor. There are a lot of valves available. Okay, butterfly wall, diaphragm wall, wall, gate wall, globe wall, angle wall, etc., etc. Right. So depending upon your piping isometric, you can choose the wall. If I want to go for say flow control wall, it is available. Pressure control wall, it's available, right? Then the check walls. So there is swing check wall, there is tilting disc check wall. Again, as per your piping ISO, you need to select the appropriate check wall. There are some general resistance like say filter is there or say a cyclone is there. So it will do the calculation for that as well. Then the size change. The orifice thin, then thick orifice, then inline nozzle. Then there is venturi tube. There is reducer. Reducer means let's say 6-inch pipe you are connecting to 4-inch pipe. Then you need to use this. Okay, and vice versa. If there is any abrupt size change, you need to use this. It can do PSV sizing. It can do this rupture disc or bursting disc sizing. So that calculation also can be done by FluidFlow. Then there is this heat exchanger. Like say if I want to find out pressure drop in the shell side, shell and tube heat exchanger, the shell or say tube side, so that can be calculated. If it is PHE, okay, that can also be calculated. So that was all about the horizontal model pellet. On the left side, there is vertical model pellet. So let us say if I click on the pipe, right? So the pipe is selected. So I can draw this. So unless and until you click on this selector, that pipe will not be, it will not be inactive. You have to click on this selector because then only you'll be able to input data in the data palette on the right side. If you want to select, then there is a selector. Okay, there are two selectors available. If you want to provide some text for your model, so you can go for text tool. If you want to increase or decrease the size of any icon, then you can use resize tool, and other options are also available. If you see, by default it is orthogonal view. See that? If I go for isometric, then this diagram would look like isometric. Okay, I'll go back to orthogonal, and other options are there that you can explore yourself. Let us go back to the problem. So what problem we have? We have these two known pressure boundaries, right? Then we have got one junction, bend, and we have got two pipes. Okay, we'll consider this as steel pipe. So let us go back to this, go to boundaries, then select known or assigned pressure. First look at my screen, then you can do it on your own. So if you see, I have clicked on the flow sheet and this still it is active. This known or assigned pressure is still active because I needed second one. So I use the second. Then go to the junction. In junction, I selected bend. So somewhere at the right angle here, I'll select that, right? Bend is still active. I'll go to pipe now. I'll use the first one, steel pipe. Now we need to connect. So I have selected this pipe. Then when I hover over this one tank, you'll see that there is a green tick. So left click, go all the way to the bend. Once you see the green tick again, you'll click again, left click. Then again, same thing you'll do from 3 to 2, right? So now we are given all the, means your model is complete. Okay, now you need to provide the input parameters. And you can see the pipe is still active, right? So that's when we will click on the selector. So that pipe will be inactive. So once you have selected this arrow, then you can click on the tank, first tank. And on the right side, if you see, there are few tabs. Messages means if you run this and if you have got any problem in the model, okay, or the errors, so the warnings and the errors will be populated in methods, messages tab. All the input parameters will be provided in input tab. Results will be made available in the results tab. If there is any chart or plot applicable for that particular item, so it will be available here. And the list would be, so whatever item that you have drawn, so that will be listed here. Like say you have one junction, right, which is bent. Then you have pipes, two pipes are there. So all the tag numbers will be also made available, and the boundary. So there are two boundaries, known or assigned pressure, known or assigned pressure with the ID or the tag number. right? Can go back to input. All right. So please draw this and tell me if you have any problem. If you have any query, please ask.
Yeah, sorry. This ports, these ports, how did you start with it? What did you click to get you those ports?
This tank, right? This is boundary.
The tanks, yeah. Okay, boundary.
So boundary, then the first one, known or assigned pressure.
Okay, sorry, same.
Once you have drawn this, please write drawn in the chat box.
When you click it, what do? You drag it down
To get what, sir?
to bring the ports.
Yes.
The tank, I mean.
If you go to the boundaries, then click on known or assigned. Then click on the flow sheet, click on the flow sheet.
Okay. Mine is not responding. Okay, I have to go to flow sheet first.
Yes, have you opened this? Created a new one?
Okay, wait.
Dr. Joseph asking, how can I split my screen? I don't quite get.
Hi, I mean the half of the screen, the presentation, and the half of the screen, the software.
Okay.
Because I try here with Windows.
You mean something like this?
Yes. How do you do that?
So you can drag this and put it on the left side.
Okay. I try
But I would prefer you keep it full screen in your system also. So while you're listening to me, that time you can open Zoom window. And while you're actually doing this, you can use the full screen in your system.
Okay.
Sorry, I'm not seeing my scale there on my sheet. Can I share my screen so that I can
Yes.
and correct it?
Yes, sir, please.
Okay. You see, I'm not getting the graphical face I'm supposed to have here.
Yes, because you are not created a new file, sir.
Okay, new. All right, good.
All right, we'll continue in your system. So you already selected boundary at C. So click and click. Click, then click. So two tanks you are selected. Then if you go to junctions, there is bend. And click here somewhere at the right angle. Then there is this pipe. Steel pipe, first one I'm taking. So from 1 till 3 and from 3 till 2. All right, then since the model is done, you can click on the selector and you can drag this bend to down so that it becomes.
Okay.
All right.
It's okay. No,
is it done, everyone?
Done.
Okay, I'm sharing my screen again. Okay. So as per the problem statement, what information we have for tank number 1? We know the elevation. Okay, so you click on this tank number 1. Then in the data palette, right side window, click on the second tab, that is input. Then click on elevation, which is 2 meters. So for elevation unit also, we have got a big list. Okay, but whatever default meter is there, that is good enough. Then pressure model. Pressure model, there are two options, static pressure and stagnation pressure. So stagnation pressure is equal to static pressure plus velocity head. right? So more or less those values will be same, but I'll stick to static pressure. Then pressure 1 atmosphere, we don't want to change it. Temperature 15 degrees C, we will not change it. Fluid is water. We'll see later how to change this one in other problems, but here no need to change it.
Ajay sir, just a minute. How to make that input for one?
Yeah, you need to go to vertical palette, left side, click on the selector, then click on tank number 1. Then click on input, change elevation to 2 meter, pressure model to static pressure. So only two changes you need to do in tank 1.
Okay.
Yes, sir. Yes, Ajay, is it done?
It's done.
Yes, sir. Done.
All right. Now let us move to the other tank, tank number 2. So elevation is still 0. Okay, we don't want to change it. Pressure model, we want to be inconsistent with the other tank. And the pressure, since this also is ambient pressure tank, so 1 atmosphere is the correct pressure. So only one changes we did, that is pressure model. We changed to static pressure. Yes, Yakesh, is it done?
Excuse me, sir.
Yes, ma'am.
I think something has gone wrong with my drawings. Can you please help me?
You want to share your screen, please?
Oh, God.
Yes, ma'am. What happened? Drawing looks okay.
Is this connected, sir?
Yes,
Are the
you need
tanks
to.
connected?
Yeah, it is connected, but you need to now click on the selector, left side vertical palette.
The number for here is 1 and 2 in your drawing, minus 2 and 3.
It doesn't matter. Vertical palette, that arrow. Okay, now click on tank 1. All right, so input, you already given that. Okay, go to second tank. So this pressure model should be static pressure, not stagnation. Then click on the bend. So bend elevation is 2 meter.
2 meter.
All right, I'm sharing my screen now. All right, the elevation is 2 meter for that bend.
Yes, sir.
And there is this, yes.
Can I share my screen? I just closed up everything and I'm still searching for the vertical palette.
Okay, share.
Sorry.
Okay, what happened? I can see vertical palette, left side. And that bend doesn't look like a bend. Okay, please click on that arrow selector. All right, so this item number 3, can you just try to drag it little up? It is just to check whether it is connected or not. So it is connected. Okay, put it back. Okay, you can click on the item number 3 and delete it. Control delete, shortcut. First select, then control delete. All right, click on this 2, then delete, control delete. All right, go to junctions. Okay, bend. Okay, select pipe. Okay, to the connection. From 4 to from 4 to 2, sir. There is undo button also, Control Z. Once you see that green tick, so that means you are good to go. Okay, click on that arrow selector. Okay, click that open pipe what you have drawn below the second tank. Okay, Control delete. All right, so click on first tank. So 2 meter static pressure. Please do the changes. You can maximize that window.
Flap it over.
You can maximize this window, right? And this is hidden here. So I'll just put it on the right side. All right, so click on this. So you are in input 2 meter elevation, and pressure model would be static pressure. Then go to the other tank 2. Elevation is 0, no change there. Pressure model static pressure. Go to the bend, elevation 2 meter. I am sharing my screen now. All right, so we are at bend. So elevation already provided. Now if there is a bend, you need to have the pressure drop calculation formula, right? So we have got 4 options. Either we can go for idle check or Miller or crane or SAE. So if I select idle check, then it will use one of the formulas given by idle check. Okay, the idle check also scientist, Miller also scientist, crane also scientist, and SAE is basically 3 scientists put together, right? So let us go ahead with idle check. Then what is the branch angle? As per the piping ISO, it will be say 90 degree. Then R by D ratio. So when R by D ratio is 1, what does it mean? It is short radius bend, correct? And long radius means this R is the radius of the curvature of the pipe or the bend. Okay, so when R becomes more, and for the same D, if the ratio is say 1.5 or 2, it is called as long radius. So long radius will have more delta P or short radius will have more delta P?
Short.
Short radius.
Yeah, short will have more delta P. Any idea why?
A sudden turn, it creates a large surge.
Not surge, but eddies will be formed more as
Yeah.
compared to long radius, and that will kill more pressure. All right, then let's go to the pipe. So you'll select the first pipe, right? And then select the second pipe. So how to select that? Using shift key. You select first pipe, then press shift key, then click on the second pipe. So this way you can input all the data in one book. So on the right side, if you see, the length is default 10 meter. We don't want to change it. Then the geometry, there are three options. Cylindrical means our normal pipe, what we see. Okay, cross-sectional area 5/40 square kind of pipe. Then the second one is rectangular or square. So if your pipe is like a duct with rectangular or square shape, so that pressure drop calculation can also be carried out in FluidFlow. Okay, this is again unique feature of this software. Then the third flow is the geometry is annulus. Like your flow is annular. Like you got a 4-inch pipe and outside pipe is say 8-inch. So if your water or say fluid is flowing through the space between 8-inch pipe and say 4-inch pipe in the annular space. So that delta P calculations can also be carried out using FluidFlow software. Again, this is the unique feature of this software. It is not available in other software. Then database, use database, yes, nominal size 2-inch. As per our problem statement, it is 2-inch only, 2-inch and 10 meter. Okay, but if I were to change it, then I'll click on this 2-inch, click on these 3 dots. It has got a huge library, okay, to choose from. But here we don't want to change it, so let it be 2-inch and schedule 40. Friction model, we have got 4 options. So if it is water only services, so we use Handson, right? If the fluid is other than water, then we'll go for Moody. Moody means Darcy-Weisbach equation, and in that FD, Darcy friction factor. So that will be calculated using Colebrook-White equation or using Moody diagram. Okay, for the different Reynolds number and the Reynolds number and for the different roughness, relative roughness values, it will give the friction factor FD. If you go for Moody equation, Moody diagram. If you don't want to calculate Darcy friction factors, you want to give it as an input, then the third option will come. That is fixed friction factor. And if the fluid is say crude oil or some hot oil, then Shell M.I.T has developed one equation that will give more accurate pressure drop calculations, right? But if you try to use it for water, it will give a warning in message tab. So in this case, Chirag, what equation we should use?
Williams.
Williams. Okay, why is that?
For it is we are using water here.
Okay, so
for water services we use Williams.
Why?
You just told for water services Williams.
Yes, but this Mr. Handson and Mr. Williams, they had done extensive work to calculate pressure drop for across pipe. Okay, for water. The test fluid was water. So water equation that they have got, which is very accurate for water service, right? So like say fire sprinkler system or water supply network or irrigation system. So if we use Handson Williams, we are going to get more accurate number, right? Now it has got one input C. So it depends on the pipe MOC. If it is steel pipe, then it should be between 90 to 110. This again will be given by vendor. Vendor will tell that for the pipe, C factor is 90 or 110. We'll take in between number, let's say 100. So we selected Handson Williams, then we put 100. Okay, other things we are going to skip, except this properties on flow sheet. Instead of hide, we'll make it show. Okay, alignment will keep it same bottom, and then properties. So this will actually provide a table like the one you see in HYSYS show table. So that kind of table you should see it. So what input parameters you would require, means you would be interested in. So there is input and result. If you expand input, there will see friction model. It is provided in alphabetic manner, so it should be easy to locate friction model. This is input, and in the results I want, if I expand results, I want the flow rate. So these two numbers I should get it, right? Now if you see this first table, it looks all good. It is not overlapping with the pipe, but the second one, this table is getting overlapped with the pipe, vertical pipe. So what I'll do, I'll click somewhere else and you can click on pipe, and in the input alignment, instead of bottom, I'll select left. So this way we can move it to left, right, or top or bottom position. Okay, so once you are completed till this, please write done. If you need help, please ask.
Friction model, sir. How to?
Yes, so you need to first select both the pipes. Then
Okay.
friction model. Yeah, friction model you change to Handson-Williams. Then Handson-Williams coefficient or C factor, change it to 100. Then properties on flow sheet, instead of hide, make it show. Then in the properties, there are two headings, input and results. You need to expand input, then scroll down, then select friction model. Then again scroll down for the results. You select only the flow rate or flow.
Okay.
So once it is done, everybody please write done.
Sorry, how did you select the two pipes at the same time?
You click on the first pipe, sir.
Yes.
Then press shift key. Then press click on second pipe.
Second, okay. Then after that, we change to friction. We change the friction model to
Handson-Williams.
Handson-Williams, yeah. Right. Then what's the next step?
Then Handson-Williams coefficient should be 100.
Okay. Right.
Then properties on flow sheet. It says hide. You need to make it show.
Property, okay.
Then in the
Sure.
properties, if you click, there are these three dots. Click on those. It will open a window.
Alignment, font, and property. Okay, on properties.
So there are two headings basically, input and results. You need to expand input. Then select only friction model. Okay, don't select everything. Only select friction model. In
Friction
input.
model.
And in the results, you will select
wait.
only flow.
Sorry. What happened?
Excuse
I
me.
lost everything.
Excuse me, sir.
Yes, ma'am.
Sir, I made a mistake, so I did Control Z. I pressed it twice, and all my lines are gone.
Okay, please share your screen. All right, so give me control. From here to the bend.
I cannot recover it, sir. Is it not possible to recover?
Possible to recover? No, I don't think so. There is no control Y active. So this is okay. Bend is fine. This one still it is moody. So shift key I'm pressing. Instead of moody, this will be Handson-Williams. And this will be 100.
Converge.
Then properties on flow sheet, I'll make it show.
Sure.
Then click on the properties. So there are two headings, input and results. First, expand input and select only friction model. If I want to know if I'm using Hazen Williams or Moody or some other. Then again expand results. Then in results I want only the flow rate. And then click OK. Now click somewhere else. Then click on the vertical pipe. This alignment bottom I don't want. I want it on the left. So this looks even better. You might want to increase the view a little bit. All right.
Thank you, sir.
Okay, so please save this file. And any query, anyone so far?
I see my screen now.
Yes.
Okay.
So let me control.
Yeah, take control, sir.
So what you have done, you have selected every item.
I don't know how I got to this place. After checking the inputs.
Yeah. If you see here, if you expand this, you have selected everything. So you have to uncheck that and only select friction model.
Friction model, yes.
And in the results, you need to check only the flow rate. Flow in the results. Then click OK.
Okay.
Then click somewhere else. Click on the vertical
Let me see
line
this.
and alignment. You can make it left.
Yeah.
All right.
I want to reduce this view something. I want to minimize it. Okay. All right.
All right. If you see on the top middle, there is one button called calculate.
Calculate, yes.
Yes.
Where is it?
Click on that.
Wait. This thing is blocking. Calculate at the top. Where is calculate? Calculate. Where is it? I'm not seeing it, sir.
You see that general resistance says size change just above
General,
that.
yes, side change, relief valve.
Above that.
Okay. Calculate, yes, I've seen it.
Click on that. So it will do the calculation and it has calculated that flow rate should be 3.5.
They are saying calculation error.
So it's calculation error.
At the bottom.
We go to the message. It says liquid calculation module not active. Okay, so I think you had downloaded, installed this more than 14 days ago, sir. Yes,
Okay,
Mr.
is
Mark?
that why it's behaving like that?
Yes. So can you open any folder? Let me try to help you with that.
Any folder, okay. Any new folder?
Yes.
New?
I'm pausing the recording.
Okay.
All right, so everybody please write the flow rate with unit, what you got after clicking calculate.
Okay, it has calculated now.
Yes, sir.
But it's still showing this error here at the bottom.
Let me close this and open it again. You're not saved it before?
No, I'm not. Okay.
Yeah, please save the file.
Okay, let me save it. Let me file. What is happening? Okay.
To give some name.
MA Council is coming. For save as. Fluid. Flow calculation.
Now let's save it, close it.
I'll call you back. 1 minute. Hello, are we there? Hello, sir.
Yes.
It's showing application has got an error or something. Save
I'll
changes
just close
to.
it.
Okay. Can I restart it?
Yeah, please.
Let me do that. Okay.
So this will work for another 2 weeks.
Yes, I will. Yeah, very good. It will work.
Okay, so let me open that file. So do you see anywhere calculation error or something?
Yeah, the thing is, wait.
Can you maximize this window?
Let me. No error anymore. There is no error. It's okay now.
Yeah, it's but you're getting more flow. So probably your input is not same as others. Yeah, that's what I thought. It should be static pressure.
Okay.
Then again calculate. You get 3.4167 kg per second.
Yeah,
but
yeah.
the
Okay, that's
flow rate,
correct. It's correct now. Yeah,
the
it
flow
is.
rate, flow rate unit,
Mm.
we don't like to see kg per second. So how to change this from kg per second to meter cube per hour? So you can right click on the flow sheet, then go to results unit.
Okay.
Then the third item you see there is flow. So the default unit is kg per second. Please change it to meter cube per hour.
Meter cube per hour. Yeah, let me check for that.
And the decimal place 4 we don't want. Okay, 1 is good enough.
Yeah. Meter cube per hour. Yeah, I've sent it.
No, wait, sir.
I've
Next to
done
that,
that,
there
but
is
maybe
decimal place. Instead of 4, you can reduce it. You see here? Here.
okay. Let me see. Flow
One is
decimal
okay.
place.
Then click OK.
Yeah, it's decimal place is 1 now.
Yes, so click OK.
Okay. All right. 12.3 meter cube per hour.
Okay, so once it is done, everybody please write the new flow rate with new unit in the chat box. Okay, so if I want to change the friction model from Handson Williams to Moody, so I need to select both the pipes. Right, please do that. Select both the pipes using Shift key.
Select what? Which pipe?
No, not that pipe. This pipe. Using Shift key.
Okay, number 2.
Yes, select both the pipes. And instead of Handson Williams, we'll use Moody.
Yeah, okay. Okay. Then we calculate again.
Yes.
16.5.
Yes, that's correct.
Okay.
Anyone who is not getting 16.5? All right. So if you actually see this system in place, like so 2 meter elevation difference is there. And there are 2 pipes, 10 meter, 2 inch. Okay. connected by 190-degree bend. Then that flow rate, the actual flow rate, will be close to 12 meter cube per hour or close to 16 meter cube per hour. What do you think?
Close to 12.
It will be close to 12 because Hazen-Williams will give you
Accurate answer.
more accurate value as compared to other equations, because Hazen-Williams equation is more accurate for water services. Done. So you can save this file and close it. I'm sharing my screen. So
Okay.
this was the simple stuff, right? Now let us do something more more complicated. So we'll now size or design a cooling water network system.
Cooling
Right.
water network. Great.
So cooling water network means you got a cooling tower. Right? So from the bottom cooling tower basin, we'll take the water suction to the pumps, cooling water supply pumps, and those pumps will send this water to different heat exchangers in the plant. The objective of having this cooling water is it will take some heat out of process fluid. Like say benzene is there as a process fluid, you want to cool it down from 90 degree to 60 degrees C. So that cooling will happen because of cooling water, and in turn the cooling water temperature will increase from say 30 degrees C inlet, it will go to say 40 degrees C, and that 40 degrees C water will be sent to the top of the cooling tower, and it will be sprayed down. And on the top of the cooling tower there will be a fan. Okay, mostly ID fan will be there, induced draft fan. It will suck the air, ambient air from the bottom. So there will be counter current. The water droplets will fall from top to bottom, and air will travel from bottom to top. So while this this water is going down, air is coming up. So there will be mass transfer. Some water will get evaporated, and because of that, that heat will be taken up by for the evaporation, and the water in turn will get cooled. And the moist air will go out of the cooling tower because of the fan, right? And the water, when it drops down, it will be like say 30 degrees. So accordingly, the cooling tower vendor will design it. And again, the 30 degrees C water will be sent to the cooling water supply pumps, and the same cycle will get repeated, right? So there is another picture of this. In this case, we have got 3 cooling towers, city 1, 2, 3. There are 2 pumps. So normally it will be one running, one standby, right? And this water from the cooling water supply pumps is sent to this total 11 exchanges in this particular diagram, and the cooling water return will be connected in the common header, which is called as cooling water return header, and it will be sent to the cooling tower top, and the same procedure or same cycle will get repeated. So there will be some water loss in the cooling tower, or there will be one the water will be purged out or blown out from the system to maintain the salt concentration, and this cooling water makeup line will be added. So if you see this cooling tower basin is there's like a small tank to store the water. As the liquid level goes low or low, that time this level transmitter will give signal to LIC, and accordingly this cooling water makeup valve will get open, and it will fill it till the required level. Now if you consider this, let's say water tank or cooling water tank, what is the pressure at which it is operating? It is 0 bar gauge. Yes. This cooling tower basin, it is open to atmosphere, right?
Yes.
Yeah.
And when this water, cooling water return header, this line, when it gets spread okay, onto the top of the cooling tower, what is the pressure at this particular point?
Atmospheric.
It will be again 1 atmosphere or 0 bar gauge pressure, right? So we know that these two boundaries are with known pressure, which is 0 bar gauge or 1 atmosphere, right? So we are going to model this system. If you see, we have got this tank number 1, which is nothing but cooling tower basin. It goes to 2 pumps, right? One running, one standby. Those are cooling water supply pumps, and this sends water to these 3 exchangers, right? There are 3 exchangers here, and the temperature change, it says 10 degrees C. So an inlet is 15 degrees C here, and the outlet is 25 degrees C. So this 10 degrees C temperature rise is happening across the exchange, right? We are going to model this. So what information we require? What items do you see here? So 2 tanks, 2 pumps, and 3 exchangers. Okay, let us draw this. Earlier file, you can close it. Okay, so on the top, if you see, there is this the view default is 80%. So I would change it to 60% so that we can fit more items in this flow sheet. So the first one is the known or assigned pressure boundary. So I'll put it here, and somewhere here, not at the bottom but little up, that is the second tank, which is cooling tower basin. So this boundary work is done. Then comes the pump. Pumps are available in booster. In booster, we'll go for the first one, so centrifugal pump. So somewhere here, I'll put one pump, and here another pump. So it looks little bit symmetrical. And heat exchanger is available on the last, right? And I'll use shell and tube. I'll click here. This is the first one, the second, and this will be the third one. All right. Okay, so please draw this. Once it is done, please write done in the chat box. Please save this file. All the problems we are going to solve today are already available in the session 11 FluidFlow folder as solved example from the presentation.
I'm trying to save, it's not saving. It's terrible.
Did you give file name?
I'm going to file. I click file. Okay, maybe because you have control, I don't know. I click here. Yes. So it's not saving. Maybe you have control, that's why.
I don't have control. I'm sharing my screen, sir.
Oh, this is your screen?
Yes.
Oh, sorry. No wonder.
All right. So once it is done, please write done. If you need help, please ask. So let us proceed. Now in the problem statement, in the pump suction side, how many pipe segments you see? You see this one, then 2, then 3, then 4, and 5, right? So we need to draw 5 pipe segments. So I'll go to pipe, I'll use steel pipe, first one. First listen, just watch what I'm doing. Then you can do the same. Now from the bottom tank, I'll start and go to, let's say, 3 dots on the right. Right? So you can see there is one open pipe. So from that open pipe, I'll draw one line up. you notice that open pipe has become a bend. Again, from the other open pipe, I'll draw one line to the pump, and that open pipe also became a bend. Then from this bend, I'll draw one line down. That bend has become now a T. Similarly, open pipe to the pump. All right, so how many pipe segments? 1, 2, 3, 4, and 5. And how many bends? 1 and 2. And how many T? 1. Okay, please complete this. Once it is completed, please type C. In the pump discharge side also, we'll have the mirror image. So from the pump, I'll start, click from the other pump, another line, click from open pipe to, then from open pipe to open pipe will become a bend. From bend, I'll go to the right, which will be in the same column as the first exchanger. Okay, once it is done, please type done. Now these pipes, 5 plus 5, 10, these pipes are in the pump house, cooling water pump house. Now this cooling water has to be taken to the different units, okay, different locations in the plant. So from this pipe, it will become a header. So from 14, this one, I'll draw one line up. Okay, from 15, I'll go all the way to the right. And then from this header, this is called as cooling water supply header, we'll give one tapping to the first exchanger. Then from the pipe, you give tapping to the second exchanger, and from this open pipe, another tapping to the third exchanger. So far, this is called as cooling water supply header. Okay, please complete this. Mr. Mark, how are you doing?
Yeah, I'm on it.
Okay.
I'm sorry.
Then again from the exchanger, I'll draw one line up. From second exchanger also one line up. Then third also one line up. And from this open pipe to open pipe. From this bend to the open pipe. And from this bend again to the cooling tower top. All right, so this is the complete model. Okay, if the model is done, please write done. If you need help, please share your screen. Mr. Mark, you want to share your screen?
Okay, let me do that. Yeah.
All right, give me control, sir. So first thing I
You
said,
already, you already have control.
We need to reduce this to 60% so that you can have more items.
Okay.
Right, so I'll just select what you're drawn here using this selector. Then
you can move it.
I'll draw it down, means drag it down.
Okay.
So this thing you have drawn extra, it seems. So right click and delete. This one, exchangers, you would like to keep it here.
Yeah.
Should be like equidistant. And let us keep it here. All right, so again, pipe. So from here to here, from this to this, so it became a bend. So from bend to here, and from here to here, from this open pipe to this open pipe. Then from this line, you can connect the individual tapping to the exchangers. All right, sir. So here I can notice that this one, this thing, it doesn't seem to be correct. So it is not connected, right? What we can do, we can just drag it onto this bend, then it will become a T. So you don't have to delete it.
And here is not touching well on the pump. On the pump discharge. Pump discharge. Is it okay like that?
Yes, it's correct. The red dot represents the outlet discharge.
Okay.
Discharge pipe. So same thing you're going to do for this. So from the exchanger, then from exchanger number 2, then the third exchanger. And then I'll select the pipe again. We already selected that. So from this open pipe to this open pipe. So from this bend to this open pipe. And from this bend to cooling tower top. Right. So the model is complete. Now we'll put input. So the bottom tank or cooling tower basin. So that information we'll put. Let's say elevation is 2 meters. Elevation is 2 meters. Please type the numbers. And the pressure model will keep it static. All right. So this is bottom tank. Now the other things will be same. Yes, we'll keep it same.
For tank 1, sir?
Yes, ma'am.
Sir, are you doing it for tank 1, sir? For
The
bottom tank or the top?
Bottom tank.
The bottom tank.
Cooling tower basin. All right. So bottom tank is 2 meters and static pressure. The top tank is 10 meters and static pressure.
So I have to do the second one too. The first tank. Elevation is 10 here.
10 meters.
10 meters. Static pressure. Okay.
All right. So tank data we have already provided. Then let us select all the 3 exchangers. Okay, one by one using shift key.
What is the bottom tank data?
2 meter static pressure. Yes, Mr. Mark, select all the 3 exchangers.
Shifts.
Okay. Now if you,
Yeah.
yes, already you are selected. So elevation, we are going to keep it 0, no change there. There is pressure loss model, right? So there are 3 options. So if you're on standard relationship, then it will actually calculate for the given flow what would be the delta P. Okay, so what input you need to provide? You need to first tell in the shell and tube exchanger, this water is going in tube side or shell side. If it is going in tube side, then what are the number of tubes? Okay, number of tube passes, then tube dia, tube length. So based on this information, it will calculate delta P. If water is going in the shell side, then the input will change. Right? So what is the pitch? What is the tube body? Then the number of baffles, baffle spacing, shell ID. So the actual theoretical calculation it will do. This option is not available in other softwares. If you go for the second option, manufacturer loss data, meaning vendor would tell you for given flow rate, like say 100 meter cube per hour flow rate, what would be the pressure drop? Let us say it is 1 bar. Okay. And the exponent is say 1, meaning it will be linear. If flow rate is 150, then delta P will also be 1.5. In that ratio, it will increase linear.
Okay.
Then the third option is fixed value. Fixed value means whatever may be the flow rate, pressure drop is going to be, let's say, 1 bar. Right?
Yeah.
This is not really a correct way of doing it, but still, in order to keep things simple, we can consider this. So flow rate is 100 meter cube per hour, then also delta P is 1 bar. Flow rate is say 90 meter cube, then also delta P is 1 bar. Then there is the heat loss model. Okay, there are also 3 options. So ignore heat loss and gain means if the inlet temperature of water is 15 degrees C, outlet will also be 15 degrees C. There will be no heat gain or heat loss. If I select fixed temperature change, so first thing we need to give is what temperature change you want. So I'll say 10 degrees C.
10 degrees, okay.
Right, and I need to tell what is the heat transfer direction. So what do you mean by heat transfer direction? If cooling water, if cooling water is getting heated, right? In this case, cooling water temperature is increasing. So heat transfer direction will be out of network or it will be into network.
Into network.
It will be into network because for us water is the network. So heat is going into the network. So we'll select into network. So because of this, when inlet temperature is 15 degrees C, outlet would be 15 plus 10, 25 degrees. Right? Then next is the properties on the flow sheet. So you can click on that, make it show. Okay, so what properties we want, and the alignment we don't want bottom because that will block, overlap the line. We'll go for the left. Right?
Yeah.
So here, click on properties in the input. Expand input. Yes, in input we want pressure loss constant. That 1 bar what you are given, so that we need to give as means in the box. Pressure loss constant.
Okay.
And what else we need? Flow rate. But flow rate will not be in input, it will be in results.
So
you can scroll down.
Yep.
Scroll down for the results. So that will be flow. Yeah, flow.
Then okay.
Does it? Yeah. All right. Let others also complete till this. Okay, so let's assume that we had done the Aspen EDR simulation for these 3 exchanges, and we found out that each of these exchanges need 100 meter cube per hour of water, cooling water, right? Now our pump, we have got 2 pumps there, but one running, one standby. So what will be the capacity of each of the pumps?
That's 300.
100.
It will be
300, but
300.
there are 3 exchanges.
Yes. So click somewhere else, Mr. Mark, and then select both the pumps using Shift key. Yes. Now I said click somewhere else so that you already selected those 3 exchanges, right? So you want to deselect it.
Okay.
All right. So you want to only select pumps now.
Correct. Selected now.
So in the data palette, if you see automatically size, it says off. Make it on. All right. So size
Okay.
of flow is correct. What is the design flow? 300.
Design flow 100.
300.
Sorry, 300.
Okay. Chart 5 RL, here it's -6.
Done.
It's
Now,
done.
if you see the second line, it says status. It says on, right? Means
Yeah, on.
it would mean that both the pumps are on, but we don't want both the pumps on. So you can
Okay.
click somewhere else on the flow sheet. Then select only the bottom pump.
Bottom pump.
Yes.
Okay. Looks like the 2 are still selected.
No, you need to select the bottom pump.
That's what I'm trying to do.
Okay, go to
Okay,
input, then
selected.
status, you make it off. Status, instead of on, you make it off.
Off. Okay.
Because if you notice, if you click somewhere, click somewhere, you see the difference between this running pump and the standby pump, right? So standby pump or inactive items will have this box around it.
Okay. It's understood, yeah.
So one of the objective of doing this assignment is to do the line sizing. Correct?
Yeah.
So we need to start with some numbers. So let us select all the pipes together.
All the pipe shipped.
Or we can do this quick way. So if you go to this edit on the top left, there is file edit is there. Click on edit.
Edit.
Then select pipe.
Okay.
So this way, usually I wait while you have completed 50% or more, then I tell this, so that you would have more appreciation for the short.
This software is very good. I think I'm going to get it though, honestly. I'm going to get it. 2 weeks. 2 weeks is not good enough.
Okay, so length we are going to change for all the pipes. So length you can change to 2 meter.
The length 2 meter.
Length 2 meter.
Okay, per pipe. Wait.
Each
Length
segment
unit
is
is meter. Length is 2.
2 meter. Then nominal size default is 2 inch. We'll make it 12 inch. Schedule 40.
12 inch.
12 inch. Click on that. 2 inch. You'll see that 3 dots. Click on that. It will open a table. Scroll down. Scroll down. So you'll see that 12 inch is there. You need to expand that 12 inch. Expand it. And scroll little down. Schedule 40 will be there. Yes. Then click OK. Then since it is water system, pressure model will be Handson Willis.
Yeah.
100 Hazen-Williams coefficient.
100. Okay.
All right, that's it. Let others also copy this. So once it is completed, till
Let me
this
save it
point,
as well.
you please write C in the chat box.
For the heat exchangers, what should be in the input?
Yes, for heat exchangers, okay, I'll open that. So for all three, it is delta P, pressure loss constant is 1 bar, fixed temperature change 10 degrees C into network. And properties also you can check. It is pressure loss constant and flow.
Pressure loss constant. Okay.
So, Madhu ma'am, is it done?
Yeah, it's done.
Yeah.
Yes, sir, I've done it. I'm confused with the flow where we typed the 300 for the pump.
No, as I said, each exchanger, the separate calculation maybe in EDR we have done, and we have found out that we need 100 meter cube per hour cooling water to be sent to each of these exchangers. So the total is 300
Where should I give that input, sir?
in the pump. So you need to select both the pumps. Then automatically size would be on. Then the design flow 300. That's it. And once you are done that for both the pumps, you want to keep one pump off. So you can keep the bottom pump off. The status, if you see, it is not on. It should be off. Ankur, is it done?
Click.
Ankur, Vivek. So a lot of radio silence from their side.
Yes, sir. I'm here. I'm traveling.
Okay.
I'm on mobile.
All right.
Yeah.
Now this 2 meter pipe length or pipe segment length and 12-inch diameter, that is applicable for this pump suction, total 5 pipe segments. Now we need to keep on editing the other things. So let us select these 5 pipe segments, mirror image of the suction. These pipes are still in the pump house. So the length, we'll keep it 5 meters. Yes, Mr. Mark, make it 5 meters.
Okay, so 5 meters.
And the nominal size, since it is pump discharge, it would be lesser than suction. So let us say 8-inch, schedule 40.
8-inch.
Expanded. Okay. All right. Other things we already changed, Hazen-Williams and 100. So that is the reason we had selected all the pipes, so that we don't have to change it each and every time. Right? You need to save time. Okay. So this part is done. So total 10 pipe segments we have covered. Sorry?
We will change only the discharge piping to 8-inch.
And length will be 5 meters.
Length. Okay.
All right. Now let us select the headers, which the pipe is already left the building. So 1, 2, 3. These are the cooling water supply header, and this is the cooling water return header, right? So this length would be 50 because it has to travel distance from one unit to the other unit. 50.
50 meters.
Yes, and it will be 8-inch, schedule 40.
Okay.
All right. Now there are total 6 pipe segments around the exchanger. Okay, inlet to exchanger and outlet from the exchanger. So please select those 6 pipes.
The
Exchanger, heat exchanger.
okay. Inlet and outlets.
Yes, correct. Using the shift key.
Okay.
So this will be 10 meters and 5 inch schedule 40.
How many inches?
5 inch.
5
schedule
inch.
40. Yes.
5 inch is not a standard pipe.
Yeah, but we are going to use that.
Okay. All right.
It's not standard, but still sometimes we use it. Scroll up. Yeah, schedule 40. Then, okay. All right. So piping data also we have provided. If it is completed till this point,
The length is okay, 10 meters.
yes.
Okay.
If it is done till this point, please type done in the chat box.
Can you show the data on time, sir?
Data, which data?
The 5-inch line data.
Yes. So inlet and outlet will have 10 meter and 5 inch schedule 40.
Okay, done.
Okay. Now this pipe, okay, this is the pump suction. And this pipe, it is pump discharge. So for the both pipe, I want to know the velocity. So if you go to properties on flow sheet for only for those 2 pipes and make it show. Okay, bottom is fine. The properties. Yes, click there on the right side box. Yes.
It's not showing anything. Okay.
Yeah.
All right.
All right. So we want the velocity, right? So
Velocity.
we have got in velocity and out velocity in the results. In velocity means inlet of the pipe. Out velocity means outlet of the pipe. So we can select out pipe. Then click OK.
Let me be sure whether the other one is ticked. The inlets. Inlet velocity. It's not ticked. Okay. All right.
So since it is liquid, in and out will be same.
Yeah.
So we can select only out.
So I can leave the other one.
All right, we can do that. So let us say OK.
All right.
All right, please complete this. Please make sure that you are saving the file in between. Okay, so now just look at my screen.
So what's in the result, sir? How velocity other one is?
Results in velocity and out velocity. Okay.
Velocity
Ma'am, are you asking something?
No, sir.
Okay. So for some time, I'm just going to make this hide. Okay, you don't have to do that. All right. Now, if you see this T, first T, it has got this red dot, which is pointing towards pipe number -4. Okay, -4 is the red dot location is towards -4. So that is what is shown here, right? The question is, what is the right location of this red dot? So some help is available. So if you click on the T, then go to the input in the data palette and the nomenclature. There is explanation. Okay. Then click on that. So one window will open. So there are two tabs, combining flow and this dividing flow. Now in this case, this pipe 1, inlet pipe, right? So it is because of the T, the flow is getting combined or divided?
It's divided.
It is divided. So we'll go to
Yes.
second tab. So diverging or dividing flow. In this option also, we have got two options here, T and Y. Now just imagine you have got this header, 12-inch header is there, right? It is traveling horizontally. Now there is this pump A and pump B. So we need to divert this branches to, one branch goes to the pump A, other branch goes to the pump B.
From B.
So what will the alpha angle? It will be 180,
Yes.
right? We are not going to take like say 12-inch header straight pipe like this in T. We are not going to have this 12-inch channel, 12-inch straight pipe, and you are going to take up tapping of 12-inch.
Yeah.
Okay, it is not going to look like that, right? It would be something like Y. Like say channel is there, 12-inch pipe is there, and we have got two branches of, and the alpha is, it is symmetric. So our system represents T or Y.
Okay.
Okay, it represents Y. So in Y, the red dot should be towards pipe number 1, inlet to the T. So we need to correct the red dot location. So how to change that? You'll click on the T, then go to this branch pipe. So if you click once, the red dot shifts to the other pipe. If you click again, then it goes to the left side. So this is what we need. So why this is important? Because you are using idle check, and idle check wants this red dot to be specified in a specific way.
Okay.
Okay, then next T. We'll move to the next T. Here also same thing, but in this case, the flow is getting combined. So if I go to the explanation, flow is getting combined. Like say pipe 11 is there, which is coming from pump A. Pipe 12 is there, which is coming from pump B. And because of this T, it is getting combined, and on the right side, it goes out as a common header, right? Now this represents a T or a Y, this system.
Why?
Y only.
It's still a Y,
Because it's
yeah.
alpha, it is 180 degree would be there, alpha value. Right? So branch 1, branch 2, and then it becomes this channel. So in this case, the red dot should be towards the header. Right? Okay. So it's already towards the header, so no need to change there. Correct?
Correct.
Okay. So let me reduce the view a little bit. Okay, let me go up. Now the next T. Okay, I'm just going to change the scheme a little bit. So if you see this pipe 14, it is 8-inch. 15 also 8-inch. Now from this 8-inch straight pipe, we are taking tapping. Okay, or this branch of 5-inch. Right? And with some alpha angle. So it could be 90 degree. Right? So if I click on this T and again go to the explanation, here flow is getting divided. I'll go to the diverging. Now this system represents what? A Y or a T? You have the channel or this header 14, 8-inch, and it is a straight pipe. From the straight pipe, you are taking 5-inch branch out.
Still a Y. It's still a Y.
No, it is not a Y. It is a T. Because see, sir, this 14 number pipe and this 15 number pipe is basically one straight pipe, correct? Which is represented here, channel and straight. Okay. It's a straight pipe. From the straight pipe, you are taking, from this 8-inch pipe, you are taking 5-inch branch out.
90 degrees, okay.
Right? So this branch and this straight pipe, they are not symmetric. Clear? So it doesn't represent a Y, it represents a T. So in this case, the red dot should be towards the branch. So what is the branch here? This 5 inch length.
Yeah.
So is it correct? So already it
It's
is
in
correct.
order.
So same funda will be applicable for the combining because the other side also we have got a T. So there also, if it is coming from any branch, then the red dot would be towards the branch. Clear? Okay, let us move to the next T. Here already it is correct. This 8-inch pipe, 8-inch pipe, and then branch is 5 inch. If you go to the other side, this is 8-inch pipe. This is 8-inch pipe, and the branch is 5 inch. So the red dot should be towards the branch because this is a T, not a Y. So how to change that? Click, click. Same goes here for this T. All right. So let me reduce the view again. All right. So everybody has completed till this point. With the table, I'll make it show for the pump suction. Yes, Chirag, is it done?
Yes, sir.
All right. So please save this file. Again, all the input. The only thing remaining is click calculate. All right. So everybody, please write the flow rate of the first exchanger.
136.4.
136.4.
Okay. And the second one is
Second one is
86.
86.8.
And the third one is
76.8.
76.8.
okay. But we wanted 100 meter cube per hour, right?
Yes.
Yes.
Okay. So why we are not getting it? Ajay, it should be 136.4. Maybe the input is not correct in your case. Okay, nevertheless, we'll proceed.
But I'm sure the total will be the total will give you 300.
It will be 300 because you are telling the pump to push 300. Yes, Madhu ma'am, what do you think? Why the flow rate in the first one is the highest, second one is less, and the third one is the least?
Sir, usually when a flow comes through a pipeline, the first pipeline will have less pressure drop compared to the second one and compared to the third one. So the first one flow will be high, second will be little less than that, third will be little less than that.
Okay, good. So if I consider this rectangle, okay, another this loop. So which T or band has the maximum pressure? The first one.
Yes.
Why? Because it is very close to the pump. Right now, while it is going from this T21 to T23, it has to travel this 50-meter distance, right?
Yeah.
So by the time this T is reached, the pressure also has got less. So this second T will have less pressure than the first T, right? And again from this T23 it goes to bend 22. It has to travel again 50 meters. So 22 bend will have less pressure as compared to T number 23. Right? And it has to travel this 10 meter, then 1 bar is getting lost in the exchanger. Again, delta P in this 10-meter line. So bend number 26 will have less pressure as compared to bend 22. Now from here, again, 50 meter it has to travel to go from this bend to this T. T number 25 will have less pressure as compared to 26 bend. And while the water is flowing from 25T to 24T, because of the pressure drop, T number 24 will have less pressure. Meaning in the entire rectangle, Okay, which loop had the maximum pressure? This T
This
would have
one.
maximum pressure, and this T would have
The
minimum
least
or the
pressure.
least pressure. So, in other words, which loop would have maximum pressure differential? The first one.
First one,
So you know that more pressure differential means more flow.
more flow.
More flow.
Flow happens because of pressure differential.
Pressure difference.
So the first one has maximum pressure differential, so it has to have more flow, right? Second one has got lesser than the first, so it has got less flow. And the last one is having less or least pressure differential, so that's why it has got the least flow out of these three, right? This is very important step because this problem is very common, water imbalance problem in any operating company for the cooling water system is extremely common problem. We recently completed one project for Bharat Oman Refineries Limited in Madhya Pradesh in India. So they had got 170 heat exchangers. Okay, we modeled the entire cooling water system for their refinery. And first step was to establish the existing system, right? Then what is the problem that they have got? And once we have studied the problem, once we have found out the problem, then comes the solution. Okay, remedy part, right? So in this case, what you have done, you have found out, okay, the problem is there. That is because of pressure difference is there. Pressure differential is not same in each of these three loops. Okay, now the problem you know, right? So what is the solution?
We should throttle the cooling water flow to the first one.
Okay.
We have to
Usually is done at the
reduce the
downstream,
line size
not
after
the substance.
each branch.
But yes, what you are saying, ma'am, is correct. That is one of the solutions. So we'll have a globe wall, manual globe wall at say line number 20, then line 21 and line 22. Okay, so that is one of the solutions. Any other solution?
Instead of connecting at T number 15, we can connect to second heat exchanger that line.
Okay, so you are saying that from here we need to connect to here.
Yes.
Okay, so will that solve the problem?
Equal distribution will be there.
It will reduce the difference anyway.
Yeah, but will it solve the problem? You're not supposed to reduce the problem. You're supposed to solve the problem. Will it solve the problem? Yes, no, Ajay?
I should think so.
No, it won't solve the problem. So that's why this is not the solution we need to.
We put the control valve.
We can. So what ma'am has said, using globe wall, she had suggested a cheaper option. You are suggesting expensive option, but yes, both are the options. Dr. Joseph, you are saying something?
Yes. 30 years ago, in a problem like that, we used restriction orifice.
Yes.
Because the people in the plant could, but they don't have time to adjust ball valve. So we decided to put restriction orifice.
Yes. So that is
yes.
So
that's
instead of any flow control wall or manual globe wall, so these three lines could have restriction orifice, right? So we'll simulate that. But any other solutions that you might think of? So we're getting less flow in these two segments, right? So why don't we have booster pump for exchanger 2, exchanger 3? So it will suck more flow or excess flow from first loop and give it to the second and third. Will it solve the problem?
Different diameter of the piping.
But it's not the standard cooling tower systems. Cooling tower system does not have booster pump like in the refinery. You know where we have cooling towers that I'm very familiar with. Apart from the main pumps, there are no other pumps.
No, booster pumps are. It's not uncommon. Booster pumps are also there. let us say some at remote location, there is some no, the cooling water requirement is there, and you don't want to have a separate cooling tower and cooling water system only for that particular system. So you can always have a booster pump, okay, which is connected to the main cooling tower or from the header. Yes, but booster pump will solve the problem, but it will be expensive. That's why we will not go ahead with that. Dr. Joseph was telling you can play with the pipe diameter. So here we have got 5-inch pipe. It'll have some delta P. Okay, if I go for say 8-inch pipe, so there will be some less delta P, so that it will push a little more flow. But again, it will be expensive option. So that's why we will not go ahead with that, right? Yes. So let us proceed with putting one restriction orifice in the outlet. But before we do that, let us see this number. What is the velocity in the pump suction and pump discharge? Okay, so 12-inch suction and 8-inch discharge, pump discharge. Is it adequate, acceptable? It is, right? So
Yes.
what is the line setting criteria for centrifugal pump suction and discharge, Ajay?
Typical velocity shall be 1 meter per second.
Okay, for
The
pump
suction.
Discharge, it should be 2.7.
2.7. Very good. So we are close to that number. All right. So 12-inch suction and 8-inch discharge is acceptable, right? Okay. Now let us put one restriction orifice. So where to get it from? So it is available here. Size change. Okay. So there are different options. We'll go for thin, sharp, edged orifice. Then somewhere in the middle, you need to click. Then here also, and then here also. So once you have provided all three orifices, you can click on the selector. Right, please select all the orifices.
Which
In the size change, first one.
Okay. You all selected?
Yes, selected, then automatically size, you can make it on. Make it on. So you're going to size for flow. So what is the flow rate you need through each orifice? 100.
Yes.
All right, then properties on flow sheet will make it show.
Do I show it?
Yes,
Yeah.
show.
Sir,
Yes, sir.
I'm actually not able to simulate the first part only. Like the heat exchanger flow is not coming out to be correct.
Okay. Can you share your
Yes,
screen? Go to the messages. All right. So it says high pipe velocity. So you have not changed the diameter. It could be a still 2-inch.
Okay, the red pipes only.
Okay, go to input. Let us see. Yeah, see, I told you it is 2-inch. So first step is also not completed, where I had told to use Hazen-Williams for all the pipes.
Yeah, instead of Moody.
Sir, I did for all the pipes I used.
Yeah, but I could see that for this first pipe itself, it was not. Yeah, see, it's Moody. And then coefficient also. Just 1 second, we'll do the other way. Go to edit. Yeah, pipes. So here you see Hazen-Williams. You change it to Moody. Okay. And then again change back to Hazen-Williams. And just put 150, type 150. Enter, again put 100. enter. Just click somewhere else and check whether the changes are done or not.
Yes, but sir,
Okay.
previously also I did the same way. I put Heathen Williams and 100. I don't know why it was not picking up.
All right. So this size we can put it 12-inch for the suction side. Select all the pipes in the suction. Yes, so 2 meter length.
12-inch, schedule 40.
See, length you can put 10 meters. Okay, enter again, type 2 meters. Okay, then this you make it 6-inch, schedule 40. Then again change to 12-inch, schedule 40. So there is this way, or you can do it one by one. Before schedule 40 first. Have you selected? No. Okay, now again change back to 12-inch, schedule 40. Okay, just check whether all the pipes are now okay. Click one by one. 2-inch, 12-inch, okay. Okay, this is done. In the discharge, 8-inch, just check quickly.
Yes, sir.
All right, run it. So there is one 2-inch I saw.
5-inch. I don't know.
No. The second
Somewhere I saw
exchanger
50
outlet.
meters.
Second exchanger outlet.
Yes, sir. These are also 5-inch. Are they supposed to be 5-inch?
Second exchanger outlet is 2-inch, no? So make it 5-inch.
Okay.
So the pump discharge length is 50 meter.
Pump discharge is first five pipe segment, those are 5 meters. Then other segments in the header are 50 meters. So in his file from pipe number 11, it is 50 meters. All right, we can run it now. Go to messages. Okay, click on that -13 pipe. Where is that pipe? -13. Click on that. What is? Go to input. Input. Okay. Why it is 50 meters? It should be 10 meters. Okay, check for others also. 10 meter, 5-inch.
5-inch, 10 meter, 5-inch, 10 meter.
All right, give me control.
Given, sir.
Check one. This is okay. Then pump, we are pushing 300. This is closed. This T I had told to make it on the left side. This pressure drop I set 1 bar, not 1 Pascal. That is the reason I had put this table so that easily we can find out. Right?
Okay.
Make it left, and I had told to use the entire space. Okay, so 1, 2, 3. This should be 1 bar. Then run it. So go to messages. Low pipe velocity, it says, what's the problem? What is fixed temperature change? I said ignore it. Again, many other input systems. 10 degrees C, this is okay. Sir, this is not 2-inch. Eight-inch schedule 40. What about this? Eight-inch schedule 40. And the length was 50 meters. This also 50 meters. This is fine. So there is this function here. This one, show flyby. If you select that and just hover over here, okay, you can see the different input. Right, 15 degrees C. This one is elevation 2 meters. Okay, elevation is not given. Yeah, it is given. Then the pump data, right? So again, you can calculate. You are getting 136, 86, and 77. All right, so I saved it.
You also didn't get the answer.
Okay, so did you check what all things I did? Yes, yes, please.
Yes, sir, but I think I made some mistake with the compounds here. Other things are correct.
Okay, please share your screen, ma'am.
It will be size changes. Yeah.
But what is next?
This doesn't seem to be connected, ma'am. What is this? Okay, and this pump should be inactive or off, right? And this was supposed to be on, and this one also on. This is correct. This also doesn't seem to be connected. Or is it? Your orifice is very close to that outlet. You need to occupy the entire space. There is a lot of space, right, in the model. So we're getting zero flow. Why is that? The orifice data, we are not given it yet full. All right, so this is fine. We need to provide the, ma'am, you are not connected it.
T number 27. Red dot should be on. Right.
Mm-hmm. All right, till this part, everybody has completed.
So shall I share screen? I have a doubt.
1 second, ma'am. You need to provide the this table also. So friction loss is 1, and what else was there?
Flow. The other one was flow.
Flow we are given for the exchanger, so not required. We'll make it left. All right. We need to provide the pump core data, so it's okay if it doesn't run. Yes, who wanted to share screen?
Can I share screen, sir?
Okay, after Yakesh.
I'm getting different flow rates, sir. I don't know what's mistake.
I don't see a screen, Yogesh.
There is some network issue.
Okay. So after adding the orifice, you tried calculator.
Before adding
Or-
orifice, I got different flow rate.
Okay.
It is 124, 89, 8.
Okay, that is probably because the inputs are not matching. Okay, so that we can get it corrected once you have the correct input. Shankar sir, can you share your screen?
There was no difference at all.
So what are the inputs
It's still the same answer.
for orifice?
Yeah, after
Orifice
adding the orifice.
design flow should be 100 meter cube per hour. That's it. Shankar sir, you are sharing the screen?
You always share, sir.
It's 100. It's still 100. Yeah.
I can see Yakesh. Actually, I don't see Yakesh's screen, but I can see that he has started screen sharing. Shankar sir, you try.
Sir, the friction loss I'm getting is 0 pascal, sir.
Yeah, we have to provide the pump core data. So that will do now.
For orifice, input elevation will be 0. Status on.
Which one?
For orifice input, status is on, elevation 0.
Correct.
Design flow is 100 meter cube per hour.
Yes.
That's
And then show table friction loss. That's it. Alignment left.
show table.
Shankar sir, are you sharing your screen?
Yes, sir.
Yes. What's the query? I don't see these things are connected. And this also is not connected. Okay, so this one is extra. So I'll delete it. So there is something here which is not connected. This is open pipe, right? It is not connected, sir. Okay, now it is connected. This one also same thing, not connected. Okay, now it is got connected. So we need to be extra careful while we are providing the input. Now it seems okay. Let me calculate. All right, so there is some problem in the network. Let us check the input. Where is my data palette? Is okay. 200. This one is off. Exchanger 1 bar, 1 bar, 1 bar. This is not 12 inch, sir. No, this is all 8 inch discharge side. So this should be 50 meters, 8-inch. Schedule 40. On the other side also, I think same thing. This will be 50 meters. And then in between lines for the exchangers, 5, 25. All right, so looks okay. Still, we have got some problem.
Friction model is Moody.
Okay.
But
So
even then, the difference is too much.
let me select this and change from Handson to Moody. Okay, again from Moody to Handson. And from 150 to 100. Then calculate again. Okay, still problem is there.
We've not addressed the nodes, so
Mm-hmm.
the direction of flow, the nodes. 21.
Water is going that side. That means something is not connected or what? Here it is.
Yeah, that one, yeah.
Okay. Now this one is having less flow. Why that? Why there is more delta P in this line?
So second heat exchanger T.
Second heat exchanger T.
Inlet side.
Okay.
Ups.
Flow is going properly. 1, 2, 3, 4 places. Okay. (300 cube per hour) is coming all right. This is 5 meter. This is okay. 58 inch. 58 inch. So we should have the given elevation data somewhere. What is happening in this? Why the flow rate is reduced so much? We must have more frictional loss in this line. Here it is, 2 inch. This should be 5 inch. Schedule 40. All right, let us see. Okay, so more or less it is fine. So we'll stick to that. Okay, anyone needs to share the screen? Otherwise, Mr. Mark, you share your screen.
Okay.
Can go for orifice.
Yes, so please provide orifice.
Okay, I've done already.
Okay. Now we need to provide the pump curve data. Okay, so how to do that? So there is database next to file, edit, view, then database. Click on that. Right, then click on booster because we're talking about pump. So one window will open. You can click on centrifugal pump. Okay, then at the bottom you see there is add. No, not that. Down. Don't use the scroll bar. Just see at the bottom there is add, import, load. So click on add.
Oh, okay. Okay. Okay, add.
Add.
All right.
So another window will open. We'll call it as test P5. Test pump 5.
Test P5.
Yes. Then okay. So that's the tag number of our pump. Right?
Okay.
So on the right side, if you see, there is capacity curve data, third last line. Then there is efficiency curve data here.
Yeah.
Yes.
Right,
So click on that capacity curve data. Capacity curve data. Close this window.
Sorry.
Third last line, capacity curve data. Okay, so let us put some numbers. So at the bottom you see there is add. So click 6 times add, because I'm going to provide you with 6 data. Flow versus
I'm waiting
head.
for you.
Now you need to click add 6 times. So 5 more times.
What do I add? Under flow.
You click on add.
I've clicked add already.
Yeah, you need to add 5 for 5 more times.
Okay, 5 more. Okay.
Yes, correct. Because I got 6 data points. One more.
Okay.
Yes, sir. Right. So first point is 0 meter cube per hour. Okay, that is already there. Then second line, 90 meter cube per hour, 90. Then the third one is 270, 300, 360. Then last one is 450. And the corresponding head, when the flow rate is 0, shut off head is 35, 35. Right, 34.5. 32.2. 31.4. 30. Then 28. All right. So the plot, what you see on the right side, that doesn't seem to be a smooth curve. So we can change the equation order. The second line on the top, you see there is quintic equation order. Instead of quintic, go for quadratic. If you give more data points, like more than 12 or 15, then whatever equation order you use, it will give the same smooth curve. But since we are given only 6 points, so it is acting a little strange. Now the minimum limit and maximum limit you need to provide. That is a minimum, or say preferred operating range, minimum flow and maximum flow. Let us put 30 as minimum limit.
30.
Minimum limit, not maximum. 30. And maximum is 400. Okay, you see the vertical red lines on the plot?
Yeah.
So if your pump is running less than 30 or more than 400, so there will be a warning in the messages in FluidFlow.
Yeah.
Let others also copy this.
It's running outside BEP.
Sorry?
I said once it's outside these zones, it's outside the BEP.
BEP is different concept, sir. It is preferred operating range they call.
Okay.
pump vendor will tell that the flow rate should not be less than this or more than this. Then he'll give the guarantee for the pump.
Okay.
All right. So once it is done, other guys, if it is done, please write done.
Well, click OK.
And now let others also copy this.
Okay. So,
All right. Sankar sir, is it done? If you need help, please ask.
Searching for the curve fit.
Yeah, curve fit what? You can change the equation.
Window.
You can go for quadratic.
No, for the window, exact database editor boosters.
I didn't get your question.
I'm just finding a way to open that window.
Okay. So we first go to database, then there is booster.
Yes. Gone there.
Okay, so you'll see
centrifugal pump.
you can select centrifugal pump, then click on add. Then one window will appear. Right, you will give the name. Okay, have you given the name? Test P5.
test P5. We typed it before. Okay, that's it.
All right. Then if you see this third last line here, it says capacity curve data.
Capacity curve, yeah.
All right. So this data you need to type. Once it is done, please tell me.
Sir, I have closed all the windows, but the data is saved. Ajay sir.
Yes, sir.
Sir, I have closed that windows. Okay.
Okay, there is no difference in the flow. That's what you're saying.
And so far we are not click calculate, but our data is not yet complete. You are only given capacity versus head. Right? All right. So your pump is this test P5. Shankar sir, have you completed this capacity curve data?
Yes, sir. The fifth data only I'm coming.
Okay. Please finish it first. Then we'll move to efficiency curve data also.
Yes, sir. Completed.
All right. So we'll click OK. Now the next is efficiency curve data. Right?
Okay.
So you can open that also. Here also 6 points you need to add, sir.
Okay.
So 0, then 90, second point 90.
0, second is
yeah, second is 90, 270,
third,
300, 360, and then 450. Efficiency starts with 0, then second point is 45, 73, 70, 57, the last one is 25. All right, so this looks like a pretty smooth curve, so no need to change the equation order. Minimum and
limits?
maximum limit, yes, you need to change 30 and 400. I'll let others copy this, then we'll proceed.
So this one no need to change quadratic.
Yeah, the equation order we had changed to get this smooth curve.
Quadratic is still better, slightly.
Doesn't really matter much as long as it's smooth. But in real project problem, you will not settle for only 6 points. You will take many points, minimum 12. So who would give this data, pump core data?
Vendor.
Yes, it will be given by vendor. All right, Sangar sir, is it done?
Yes, sir, done, sir.
All right, click OK. Then again OK. Then select both the pumps. All right, so you had used for the pump automatically size on, right? So that now you'll use off. Automatically size, you'll make it off. Okay, you'll see that.
Sorry.
You'll see that pump model has arrived, right? So
Mhm.
you can click on that. You have got your own pump now. Test pump 5. Type T.
Type T.
No, just type T.
Type T. Where do I type it? That's the problem.
Here, anyways, just type T. So it will take you closer to your pump.
Okay.
All right, then click OK. You are not provided the table for the orifice. We need to know what is the pressure drop. So let me select show friction loss is here, friction loss. Then click OK, and alignment we want on the left. All right, and the unit I don't want Pascal, I want bar with 2 decimals. So pressure drop unit bar and with 2 decimals.
Sorry. Pressure drop bar, okay. And 2 decimals, okay.
Yes. So this is all set. Please save it and then click calculate. See what happens.
Wow.
So
This is great.
let me increase the view a little bit.
It's great.
So the first exchanger or first loop, delta P across that orifice is 0.43. Right. Next one is 0.2 and the third one is 0.16. It also calculates the orifice size. Like the first one, click on first one, then go to results. So it would tell what would be the orifice size, which is 70.4 mm. Right?
Mm.
The same goes for here. We can put that in the table also, which I think I forgot to do that. But nevertheless, we'll continue with this. Right. So this is one way of solving the problem. And if you have not much fluctuation, too much fluctuation in the flow rate, then adding the restriction orifice is the best option. But Dr. Joseph, if the flow rate is changing, like sometime it is say 100% capacity plant, sometime is 80%, sometime it is 120%. So that time flow rate would also change accordingly. So that time a restriction orifice will not be of that much help, right? Because it is not really controlling anything. Okay, so in such cases, flow control valve, the automatic flow control valve would be a costly, but it will be a better option, right? So, okay, let us put that also in that option also we'll study. So let us select all three orifices. But before we proceed, please tell me everybody has got this.
Sir, I have missed one efficiency point number, sir.
You missed one efficiency
How to
point.
change unit of friction loss?
Yes, I'll tell you. Before that, let me go to booster. Then centrifugal pump. Test pump 5. All right, this one.
Yes, sir. Just a second. Efficiency curve data. The points. Yes, sir. Just a minute, sir.
Okay, this example is available in your the folders.
Done, sir. Done. This one is done.
Yes, somebody asked how to change the unit of the pressure drop, right? So you right click on this unit, result unit. Earlier we changed from kg per second to meter cube per hour. So in the same window below, you'll find this pressure or head drop. So you can change to bar, and the decimal place you can change to 2.
From where, sir? The unit came from where, sir?
You need to right click on the flow sheet, then click on result unit.
Okay.
We have done this earlier.
Yes,
All right. So we had the problem of water imbalance. So are we able to solve that problem? Each loop is having 99.8, right?
Yeah.
So in real world, it is 100 meter cube per hour. Okay. So who did not get this yet?
I'm getting 0.7 bar
0.7 bar. Where?
for the orifice.
First orifice. So that is probably because some input is not matching. Okay, so as long as you are getting some answer, which is okay, but you need to check that we are talking about the same input, right? So please select all the three orifices. You did not get what? You want to share your screen now?
So from where we can increase the decimal point?
Same window, right click, result units. So that unit is there, and just next to that you'll see decimal.
Yeah, okay.
Yes, ma'am. What's the problem?
After the efficiency point, I actually left the tracks.
You have created the pump, right?
Yes, sir.
This seems to be okay.
This is not 28.
So this was 30 and 400. And okay. Okay. We click here. We need to select both the pumps. Okay. So automatic size you changed. So this one should be air pump test P5. Let's type T test P5. Okay. So let me check it has happened for this pump also. Yes. So calculate. All right. So result units. Pressure drop we want in bar with decimal place 2. All right, so 0.44. So same thing you can do it for this other two also. Right? All right. So sorry.
Orifice size, sir.
Orifice size also you can add here in the properties. This is calculated, right? Calculated size for this one. So click OK. That's it. So same thing you'll do it for this orifice and the third one. Okay, everybody got this one? Mr. Mark, can you share your screen?
Okay.
But can I see the pressure at the nodal points? How to do that?
Pressure what?
Pressure at a certain point.
Yes, we can do that. You have that stagnation pressure and static pressure both.
Okay.
In other software, there is no differentiation. There is all just pressure. But FluidFlow guys, they want to make it little more, descriptive.
How to make it visible?
That pressure will be available at the nodes, at the junction, right?
Yes.
So you can right click on the junction and see in the results what options you get for the pressure. So there will be static pressure and stagnation pressure. So you can choose.
Okay, thank you.
I don't see anything, sir. It's all white background.
Yeah. Should I increase it?
I can see the window, but there is nothing inside. It is just white.
My screen?
Yes.
It's not. It's not possible. Okay. Let me share again.
Yes. Now I can see.
Okay.
All right. So let me control it. Okay. Now the question: if I convert or replace this orifice, okay, with flow control valve, like these 3 orifice, if I change it to flow control valves, so the pressure drop value what we are seeing now 0.43, 0.2, and 0.16, right? So the delta P would increase or would it decrease because we are using flow control valve?
Delta P will increase now.
Delta P will increase. Okay, Shankar
Yes.
sir, what do you think?
Delta P will increase.
Okay, 2 increase. Votes. What about others? Madhu ma'am? No idea. Ma'am, the question is clear?
Sorry, sir, I didn't listen. Can you please repeat the question?
Okay. If I replace this orifice with flow control valve.
Orifice with flow control valve.
Yes, so the pressure drop in that case across that control valve would be, say for the first one, will it be more than 0.43 bar or it will be less than 0.43 bar?
It will be more than 0.43 bar.
Okay, so 3 votes for more. Anyone else would like to answer that? Yakesh?
Yes, sir.
More or less?
Couldn't say, sir.
Why? You had to take a guess. And that should be calculated guess.
Yes.
Chirag, what do you think? Or you already said? So when we started, what was the flow rate in the first loop? 136 meter cube per hour, right?
Yeah. Yes.
All right. So what exactly we did? We used orifice because the first loop had a lot of energy in it, correct? So we just killed that additional pressure with orifice, right? Meaning, if I kill the 0.43 bar in the first loop, then the flow rate in the first loop will drop from say 136 to 100 meter cube per hour, right? And that delta P has happened because of orifice. Do you really think that the system would really care if how the pressure is being reduced with orifice, with manual ball, glow ball, or a flow control ball?
No,
Will it really matter?
doesn't matter.
It doesn't matter, right? So you have selected all the three orifices, then right click on one of the orifices.
What?
You have already selected three orifices. You need to right click on one of the orifices.
Okay.
Then there is change component. Click on change component. First one. First. Yes. If you scroll little down, you'll find flow control valve. Flow control valve. Then click OK. So the orifice has been changed to flow control. Right? So while you are still at input, we can have the properties also. Click on the input in data palette. Alright, so automatically size will make it off. Off. And the flow rate, design flow rate we want of course 100, so that will remain same. Wall model, do you want 2-inch butterfly wall or 2-inch wall in 5-inch line? Does that make sense?
No.
No, right? So one size less or two sizes less. So the line size is 5-inch, so 3-inch butterfly wall would be a better option. Butterfly wall because for water services we usually go for butterfly walls. So go to wall model. Instead of 2-inch butterfly wall, you go for 3-inch butterfly wall. Scroll down. 3-inch butterfly wall. Then click OK.
Right.
Then go to properties. Make it show. Then go to properties. Yeah. So we want to know what is the wall opening and calculated CV and friction loss. Yes, Mr. Mark. Go to the properties. So all these things you are going to get it in results. Calculated CV, friction loss, F, friction loss. Go up, 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 up. Friction loss. Okay, then go to the last wall opening. Go to the last, extreme last wall opening. So these three information we need. Click OK. All right. Let others also complete this. Then you can click on calculate. All right. So what do you see there? Any change in delta P?
No.
There should be no change in delta P. Because if you increase pressure drop, then the flow would reduce and vice versa. Okay, if you click somewhere else on the flow sheet, you see that the second and third control wall are red. Okay, so what is the problem? You can check the messages. it says wall position is greater than maximum limit. So what is the wall opening for second and third? 76 and 78. So we know that as long as it is less than 80%, we are okay, right?
Yes,
So
sir.
why this fellow is having problem? Because in fluid flow, the limit set is between 20 to 75%, but we can change that limit. If your vendor says that this particular wall can go as high as say 85 or 90, we can always change the number. So you see on the top right side, there is System International. System International. Don't click there. On the right side of that, there is yellow. One arrow is there, yellow, extreme right.
Warning and
So
hints.
right. Yeah. Warning and hints. Click on that.
So,
Go to liquid limits. So there you would see minimum operating control wall 20 and maximum operating control wall 75. You can change that 75 to 80. Then okay. Since you change the input, you need to calculate again. So this time that warning will go away because the wall opening is less than 80. Ma'am, you said something?
sir, how did these two valves turn red, sir?
Because fluid flow default maximum control wall opening is 75%. So since it is exceeding that limit, that's why it is red. But we can edit that. As I was telling, if you go to hints and warnings, you know where it is?
Actually, it didn't turn red in my sheet.
What is the wall opening?
Yes, sir.
Hmm?
Yes. For me, the valve opening, it was so one is 66.7, the other 75, next one is 78, 77, but it didn't turn red for me, sir.
Okay, you click somewhere else on the flow sheet.
Oh, yeah.
All right. You know how to increase the limit, right? From 75% to 80.
Can you
You
explain
see
it?
this? You see this warning and hints?
Warning and
Yellow.
hints.
You
Yes,
click
sir.
on that, then go to liquid limits. So instead of 75, put 80% and then click OK and run it again. Clear?
Yes, sir.
All right. Any query on this problem?
Yeah,
Also,
but
when
excuse me, if the flow is varying, where does the control valve takes its signal from? From the pump?
It will have see here what we are trying to do in this particular problem is we want to make sure that flow rate is 100 meter cube per hour. But in the real world, the control valve will be on the cooling water side outlet, no doubt. But it will be controlling the temperature. So the process side outlet temperature, there will be having temperature transmitter, and that will give signal to this TIC for this control valve. It's basically a temperature control valve, not flow control valve. But anyway, if you already decided that the flow rate is 100 and the design flow rate is 100 meter cube per hour, so we can use this to find out what is the CV, what will be the wall opening if you choose to use 3-inch butterfly valve. All right.
What is the advantage of using the control valve here, sir, when the orifice is much cheaper than control valve?
This also I had explained. If the flow is not, means the process side flow is more or less same, okay, in all the cases or all the scenarios, then you have to use flow control valve. You can get away with a restriction orifice. Now just imagine that sometime we are running the plant at 100% capacity. So that time probably the flow rate or the net flow for the cooling water is say 100 meter cube per hour. If sometime we run the plant at say 50% capacity, right? So that time what will happen if I have the restriction orifice? So do you think that the flow rate will reduce to 50? No, it won't, right? So that time we'll end up providing more water. So the process side also, the temperature will be on lower side, which may not be accepted, right? So for that, if you have the flow control valve, then it will work fine. But yes, it is expensive. That we cannot avoid it, right? So we need to actually check.
It's once in a while now. It's a project. It's just it's something you put at the installation, after which it's just maintenance.
Correct.
So it's okay.
All right. So
As
in
long as see what you
the
want.
project what we had done for Bharat Oman refinery, so they didn't have any this glow ball also for throttling purpose. They had the gate valve for isolation. So the gate valve, they are not fit for throttling. So that's why they could not maintain. They wanted to reduce or increase, but it was not really happening. Okay. All right. So let us proceed.
One more doubt.
Yes, sir.
What if we have the control wall or the restriction or base before exchanger? Will work fine?
Typically, it will be on the downstream of the exchanger. The reason being, if I keep it on the upstream, then there is a chance that I'll starve this exchanger for the water or whatever fluid it is there. So maybe if the water is going in the shell side or the tube side, so there is a chance that the shell side or tube side will not have full, liquid. Means the tubes will be filled with this liquid or fluid, basically. Right? So there could be chances of overheating or some hotspot might get generated. So because of that, we'll always keep it on the downstream, so that even if there's get throttle, upstream system, that exchanger will be always filled with our liquid. That makes sense?
Yes, sir. Yes. And one more doubt, how to make the nodal pressures? So
how to make the?
How to see the nodal pressure points?
Nodal pressure, meaning this pressure?
Yes.
So it is there. Channel stagnation pressure is there. Then, so this pressure is available, right?
Okay.
Okay, it will be available for all the. There is this out stagnation pressure, in static and stagnation pressure. So if you compare, there is not much difference in stagnation and static, because velocity head v square by 2, that value in bar is going to be very negligible, right? So that's why this fluid flow competitor, they don't really care about static and stagnation pressure. They just say that it's pressure.
Okay.
All right. So any query, any further query on this problem? Okay. So I'm sharing my screen. So this problem will be solved with orifice, with flow control valve. Okay, this we already seen. Now there is fire water network. Just imagine that you have got, say you are working in a refinery, right? Or project is in refinery, wherein you have got the storage tank for say petrol, right? And from the storage tank through the pump, petrol pump, you are sending that petrol to the road tanker. So that's the system. And you have got say six, say for example, 6 pumps you have got in the pump house area, right? If any fire incident happens, so that fire will be extinguished using say fire water, correct? And that fire water will come from fire water supply pumps, right? And it will come in the pump house. It will be sprayed from the sprinkler or spray nozzles. So you must have seen the spray nozzles in the plant, right? So there is one such example is available. Let me just make it a little bigger. Okay, so the right side area, what you see, So in this space, which is say 2 meter by 12 meter, okay, 2 meter is the width and 12 meter is the length of that pump house, wherein our petrol pumps are located. Okay. The protected area is pump house, petrol pump house. The total area is 2 into say 12, so 24 meters square. So this is the area we need to protect. So fire water requirement now is, so there is NFPA 13. That what we are actually trying to do here is to calculate the fire water demand. It is one of the most important calculation in safety studies, right? Fire water demand calculation. And good thing is it's very easy. The standard what we use is NFPA 1313. So you need to first calculate what is the total area that you need to protect. Okay, step 1, which we have done, 24 meters square. Step 2 is to get the fire water requirement norm. Now there are 2 numbers associated with it. If it is hazardous like petrol, then the number would be 20 liter per minute per meter square, right, for the hazardous services. If it is non-hazardous, then it will be 10 LPM per meter square, right? So these numbers either we can take it from NFPA 13, or in most operating companies, they will have these numbers given for this particular system. You need to use this fire water requirement norm. So let us go ahead with 20 liter per minute per meter square, meaning per meter square, you need to provide 20 liter per minute of water. Then if you multiply this 20 LPM per meter square multiplied by 24, so meter square will get cancelled, and you'll get 480 LPM water requirement, right, which is 29 meter cube per hour. So again, as per NFPA 13 guideline, you have to take 20% excess. So 1.2 times 28.8 is 35 meter cube per hour. Meaning, when there is fire in this pump house, you have to supply 35 meter cube per hour of water, right? So let us assume that you have only say 2 sprinklers, right? So total flow you are providing 35 to this pump house, right? But is it evenly distributed? No, because only the north side of the pump house will get maximum water and south side will be dry. So if I keep only 2 sprinklers on the top, on the north side, it is not going to work. If I give 4 sprinklers, so 1, 2, and on the south side also 1 and 2. So maybe on the periphery, we will get water supplied, but in the middle, we will not have any water. Clear? So we have to make sure that the sprinklers are arranged in such a way that each and every square inch of the area to be protected gets water. So what we do, yeah. So if you see this, the sprinklers will be arranged in this way. So typically the distance between 2 sprinklers is never more than 2 meters, right? And the vendor will tell that what is the coverage, spray coverage, and you have to make sure that each sprinkler, this coverage area will be overlapped. Correct? It will be something like this. So this is a spray angle and this is a spray coverage. And the the next spray coverage area will be always overlapping with the first one. So this will ensure that each and every square inch of the area will be getting water in case of fire, right? So typically what will be this piping will do, that it will prepare the top view of this area. Okay, so there will be a lot of circles and all the circles will be overlapping with each other, right? And the circle diameter will be getting from the vendor. Okay, so the sprinkler vendor. So vendor will tell that if you give minimum say 1.5 bar gauge pressure at the inlet, then I can assure that the spray area, coverage area would be, let's say 3 meter or 4 meters, whatever, right? So taking that information from vendor, piping will create a diagram, the top view, and it is our job to approve that, right? So once that gets approved, then we'll prepare our model. Now in this case, what I have done, this sprinkler to this sprinkler, the total distance is 1 plus 1, okay, 2 meters. Now this T and this junction, the distance is 2 meters, right? So meaning this sprinkler to this sprinkler also, the distance is 2 meters. So every sprinkler is distributed with a distance of 2 meters each, right? And if you see the rest of the system, it involves the fire water tank. There is fire water supply pump, one running, one shut down, right? And that goes to the header, right? Now this example is available. If you go to solved examples in the from the presentation, there is a sprinkler system, right? So let me just open that file. This example we are not going to do from scratch. We're just going to review it. All right. So let's start with the tank. So tank is having say 2 meters elevation, stagnation pressure, right? There is this suction pipe, 2 meter 4 inch. So why I selected 4 inch? Because the velocity is coming 1.3, which is not bad. Then the pump. So for pump also I provided this test fire water, right, with some data from the vendor. Then the pump discharge pipe I have taken 3 inch, inlet is 4 inch, outlet is 3 inch. And there is this deluge valve. So typically what happens, let us say this pump capacity is something like how much, 35 meter cube per hour, that is the duty flow. But do you think it is really required to keep this pump running? These are the main pumps. It is not really required to keep the main pumps running all the time. So in fire water system, there is something called jockey pump. Jockey pump are typically like the 10% of the main pump capacity. So if the main pump is 35 meter cube per hour for the same differential head, so for the same differential head, jockey pump will be about say 3.5 meter cube per hour. Again, there will be standby and the main jockey pump. So only one jockey pump will be running, and its job would be when there is no fire, this valve is called as deluge valve. Okay, this is automatic on-off valve. When there is fire, FNG system will send a signal to this valve, this deluge valve, and this valve will get open, right? When there is no fire, this valve is closed. Do you really think that we need to run this 35 meter cube per hour pump? No. So that time the main pump will be no, it will not be working. It will be off, and a single jockey pump will be working. And of course, there will be minimum recycle line, and it will try to maintain some pressure in the pump discharge header. Let us say that pressure is say I'm just putting a number, say 5 bar gauge, right? So just imagine the small pump, 3.5 meter cube per hour jockey pump is working. This deluge valve is closed, and the system is able to generate a pressure of 5 bar gauge. Okay. Now suddenly there is fire in this petrol pump house. Then the signal from FNG will go to this deluge valve, right? And in that case, what will happen? All the water which is there will try to go to the pump house, right? So what happens to the pressure? It was before 5 bar gauge. The pressure will reduce. So from 5 bar gauge, it will go to say 5.8, then 5.5. So maybe 5.5 is the set point for the main pump to start, right? So the main pump is big pump. It is already designed accordingly to maintain certain pressure and the flow rate to give to the system. So the main pump gets activated, and when main pump is active, jockey pump doesn't have to work. So it will get tripped. It will get switched off, right? So main pump is working. Deluge valve is open, so it will give the required amount of water to each and every sprinkler, right? And when there is no fire, then the operator will give signal to close this deluge valve, and this valve will be more. Normally, this auto off is not given for the deluge valve. So manually, this valve will be closed by field operator, right? So here, if you see the elevation of this is 3 meters. See, so this also 3 meters. These junctions 3 meters elevation. This also 3 meters elevation, right? All the sprinklers are 3 meters elevation, right? Meaning this entire thing is on the top, just below the roof. Okay, and the roof is about 3 meters height. Then, if you click on the one of the sprinklers, so there are different models available for the sprinklers. Like the one which you have taken here is having K is equal to 2.8. K factor means this shows the capacity of the sprinkler nozzle. If I have K say 4.2, right? Meaning for the same pressure drop, this sprinkler will give more flow. So what is the flow rate we want through each of the sprinklers? We want 2.9 meter cube per hour. Means slightly on a higher side. 2.91 is okay, 2.95 is okay, 3.1 is also okay. But if I use a bigger size or capacity sprinkler, and the flow rate is say 10 meter cube per hour, right? So will that be acceptable? No, right? Because we want 2.9. If you are having 10, that means 10 into 12 sprinklers. So how much? 120 meter cube per hour. So meaning you need to go for a bigger pump, right? Right now this 35 meter cube is working well, but now in the other case you'll have to go several times more than that. Not just the pump, but the pipe sizes for the suction and the discharge, that will also be affected, right? Because of this, we have to always optimize, right? Optimize on the sprinkler K factor. So this number will actually be given by the vendor, right? So vendor has in their catalog, so they will say that the minimum pressure upstream of the sprinkler should be some value. So in most cases it will be 1.5 bar gauge. Meaning if you want say 2.9 meter cube per hour water to be sprayed with some some reasonable coverage area, then you must have 1.5 bar gauge upstream pressure. Just imagine you got only 0.1 bar gauge upstream of the sprinkler. Do you think that water flow will be there? The flow rate what we want 2.9. It will be flow will be there, of course. There will be pressure differential, so flow will be there, but it will be 0.1 meter cube per hour, which is not acceptable, right? So that is the reason upstream of this. That is again one of the objectives of carrying out this study, that you have to ensure that if I using this pump model, then what is the maximum pressure that will be available upstream of this the sprinkler. So here, if you see the number, it is about 1.7 bar. I'll just change the unit. Pressure, not pressure, yeah, pressure drop also you can take it. Bar and decimal, I'll make it say 2. Then click OK. So 1.7 to 2 bar is upstream. If the vendor has said that it takes 1.5 bar gauge minimum, then this is acceptable, right? If you are getting something like say 1.2 bar gauge upstream of the sprinkler, then we have to go for a bigger capacity pump. Flow rate will be same, but the head would be bigger. So maybe the higher impeller size we need to go for, right? So this kind of information you can take it out from FluidFlow software. And now there is one software, as a PipeNet sprinkler is there, that does only this kind of steady state analysis, right? That cost for 6 months is something like 13 lakh rupees. 13 lakh divided by 75. So about 17,000 USD, Mr. Mark. And that is only applicable for only for 6 months, right? So that kind of study you can do it in FluidFlow with 3 to 4 lakh rupees perpetual, right? So that way it is very extremely cheap software. Okay, any query on this?
Sir, does FluidFlow can do surge calculation?
No, that they
Sir?
cannot do. The last 2 years before when we started, we had told the developer that this is the biggest disadvantage of FluidFlow, because this competitor PipeNet, it can do surge analysis. So they have got PipeNet transient software. So that time the developer had said it will be available in next 6 months. So that now 2 years have passed, and they are working on the transient. But at some point it has to come.
Excuse me, maybe because of time we may not have the time to develop it. Have you used the software to solve the problem? You can share the file now.
Which software?
This very problem, this sprinkler problem.
See, whatever we have studied, it is available in this folder, session 9, FluidFlow.
Okay.
So there is a folder here, solved examples.
Okay.
Presentation. So
It's
we have
right.
covered up to this. So we'll take one more example, PSV sizing. Then we'll stop FluidFlow and we'll talk something else, right? So let us close this.
Okay.
Close
Sir, I
all.
have one more question.
Yep.
Yes, ma'am.
Sir, you have shared in the material the PipeNet videos, right, for working in the PipeNet.
Yes, yes.
In that, have you shared surge analysis, sir? Have you done any surge analysis in that?
We are expert in the market for surge analysis. We actually recently completed a project for Qatar Gas. We did the Qatar Gas entire firewater network simulation, and they had got a lot of pipe failure issues for their GRP pipe. We modeled it and we have suggested them some remedies that to go for the surge accumulator or surge vessel. And once they implement that in the next shutdown, so their frequent pipe breakage thing will go away. At present, I don't have the software because, as I said, it's very expensive, and only 6 months duration license that costs something like 12 lakh rupees, something like say 16,000 USD, only for 6 months duration. So as and when the project comes, then we rent it. All right,
Yeah, but
but
renting it will be cheaper now, isn't it?
Sorry?
Sir,
To rent
if
it
you
will be
want to
cheaper.
show
Rent it means we get this license from Sunrise. That's the developer of PipeNet.
But
Yes,
you won't pay $17,000 if you rent it for like a month or 2 months.
There are different options, but
Be cheaper.
Any project that involves surge analysis, it never gets completed into 1 month or 3 months. You need to have to go for a longer period license.
Okay.
Yes, ma'am, you had some query?
can you share any of the surge analysis report which you had done earlier, something like that?
No, I cannot because I signed NDA with my clients. But the structure would mostly remain the same. You got the introduction, this project objective, then document objective, then the design basis, process design basis, right? And different scenarios you would study, like the existing case, what exactly is happening. Then the remedy, you use the surgeon, say air relief valve. Then you try to run it again. Okay, so if there is any positive impact because of that you noted. But mostly that really doesn't help. But we need to create it as one of the scenarios. Then we can have the surge vessel or surge accumulator at different locations, and then again we run it, right? And then that's it. So that's what we do. And then conclusion. Finally, what exactly you recommend? So if you have any query, you have prepared any surge analysis report, so I can check it. But unfortunately, I cannot share my client's files with anyone. All
Actually, I
right.
was so interested in learning that software, and I have installed it, and it is already in my PC.
Okay.
I just have to find some examples for working on.
In PipeNet library, they have got few examples. Have you already completed those?
No, sir. No, I haven't started. I have just installed it. I have to.
What
do it
version you are
after
using for
I
PipeNet Transit? I had used 1.11. That was licensed version, and a few months before. Hello.
1.8.
1.8. Okay. So, is it installed in your system right now?
Yes, sir.
Okay. Can you share your screen?
Share it.
So these solved examples will open after 14 days.
That will open, but you will not be able to click calculate. Means you can click calculate, but nothing will happen. All right. So, requested control. Yes. So it's in help. There is learning training material, English. Then there is transient module. Okay, so these are the PDF files. So this is the first thing that you need to go through, right? Then second thing is these are the PDF files. There is example data files for transient, right? So you can check all this one by one. This one is pretty interesting. So if you do all these things, you can say like you have covered like 70% of everything, right? Again, in like any software, any other software, you click here, see what happens. So that kind of approach should be there. But you should always start with the Converge example. You should have the same results what this EX1 or till loading system file is. Once you have done that part, then you are ready for level 2. Most people what they do, they start to level from level 3. So that's why they make mistakes. Then they never come to know what went wrong. All right.
My HTRA software, sir. Here also the manuals would be available for doing it, sir.
HTRA I never used, so I cannot help you with that. But I believe this solved example will be there.
Okay.
All right. So I'm
Actually, I
sharing
tried
my
solving the EDR problem whichever you gave in HTRA, but it showed a lot of errors, sir.
Okay.
It is asking too many data. Actually, Aspen is asking very less data, but HTRA is asking too many data.
Okay. So is that a good thing or bad thing?
Good thing.
All right. So let me close this. We'll move to another example, that is PSV sizing. So if you remember, we have solved this example in session number 2. Remember the mixture of N-butane and propane, relieving temperature 167 degrees C. Okay, PRV set pressure 75. And in first example, the back pressure was 0 psig, meaning PSV outlet was open to atmosphere, and overpressure was 10%. Chirag, why overpressure will be 10%?
It's a block case, no?
Yeah, non-fire case and single PSV. So overpressure 10%.
Non-fire case and single case.
If it is non-fire case and multiple PSV, then 16%. For fire case, 21%.
21.
All right, so let us solve this example. Where is FluidFlow? Yeah. All right, so this is the one. So this will be available in the boundary. The third one, that is the vessel or accumulator. Then there is this PSV. It will be available in this relief devices. And this is the tank with known pressure. Okay, again the boundary. And these three items are connected by these two pipe, right? This 32 and then 30. So let us draw this. We'll go to the boundary. Then first one is the reservoir. Click. The next is relief device. PSV. Click. Then the last one is the boundary, known pressure. Click. Then go to pipe. So I'll use the steel pipe. So from vessel to PSV, from PSV to the tank. Okay, so this is the model we need to prepare. Once it is done, please write done in the chat box. All right. So you'll click on the selector in the vertical palette, then click on the vessel. So the surface pressure, your set pressure for the PSV is 75 psig. Overpressure is 10%, so 75 into 10%, so 7.5. So 75 plus 7.5 is 82.5 psig. So I'll just write that 82.5 pressure unit is psig. So the last one is psig. Temperature inlet is 167 degree Fahrenheit. And other things we can skip it. So let us finish this one. Fluid, it says water. We are going to change this later, but for now let it be water. Properties on flow sheet, alignment left. So here I want surface pressure and temperature are given as input. So I'll check in input, pressure, surface pressure and temperature. So 2 items. All right. Once you complete this vessel part, then write C in the chat box.
So can you please repeat the parameters whichever we changed after the sketch is done?
Yeah, you click on one, that is the vessel. What is the surface pressure that I have typed with the unit? Yes, ma'am. Done?
No, sir, I have just started some line and it is moving everywhere.
You want to share your screen?
Yes, I apologize. Service contribute this thing.
You need to connect that with the pipe. So from vessel it goes to the PSV, from PSV it goes to the tank. You have not selected the pipe yet. The flow is from the vessel to the PSV and then PSV to the tank.
But sir, the flow is from PSV to tank.
Ma'am, this PSV is on the top of some vessel, right? So this gas is going to go from where? From the vessel to the PSV, right? And from PSV to this tank represents the PSV outlet condition, and this vessel considers represents the PSV inlet flange condition,
Okay.
right? So we cannot just have PSV as standalone. So that's why we have to provide this vessel and this tank.
So I should delete this one and withdraw it.
No, it doesn't matter. It doesn't matter. Just go to the tank, sorry, vessel, bottom. All right. So what is the surface pressure? 82.5. Ma'am, surface pressure. Elevation ke same. 82.5 psig. The last one, extreme. Go last. Yes. Temperature is 167 degree Fahrenheit.
Temperature.
All right. The fluid is not water, but we'll change it later. So if you go to properties on flow sheet, instead of hide, make it show. So what information we want? Surface pressure and temperature. So those are in input.
Sorry, can you go through that input information, please? For the vessel.
For?
The vessel, please.
Yeah, 82.5 psig.
That's pressure.
Yes, and temperature is 167 degree Fahrenheit.
Yeah, just hold on.
Above the
Pressure.
Above the temperature.
Pressure.
Sir, is it stagnation pressure, sir?
No. I said surface pressure. That is input. You have typed it.
82.5. 82.5 watts.
psig. You can check this.
PSIG.
It's available there.
Yeah, it should be. It's available. PSIG is available. Yes. Temperature. What other information again, please?
167 Fahrenheit.
Yeah, I've done that.
Okay, the water.
Is that all?
No, fluid we are going to change from water to the gas mixture later. Okay, so for now, we'll skip it. Go to the properties and get the temperature and surface pressure. Mr. Mark, please share your screen. We'll see that.
Okay.
Ma'am, that alignment we can make it on the right.
I see my screen now. Yeah.
Yes.
Okay.
So we are here. Alignment, I'll make it to the right. So properties I need to input. Okay, I don't want anything from the results. So surface pressure and temperature. So surface pressure is here, temperature is here. Click OK. So we are done. Now go to the next. This is the PSV inlet pipe. So this should be as less as possible length. 0.1 you can write. Length 0.1 meter.
Okay.
Okay, then nominal size you can put 4-inch schedule 40. 4-inch schedule 40. Then okay. The fission model is going to be moody only because this is not going to be water. Then go to PSV.
PSV.
The red thing on the flow sheet. You already done that, sir. Click on that.
Okay.
All right. So set pressure is 75 psig. Set pressure 75 psig. PSIG.
Yeah.
Flow rate is 53,500 pound per hour.
53,500 pound per hour.
Pound per hour. And the discharge coefficient for vapor is 0.975. Discharge coefficient.
No, this thing is covering it. I want to remove it. The talk something is covering it. Okay. Discharge coefficient is what?
0.975.
Right.
And then properties on flow sheet, that let it be 1. Properties on flow sheet, make it show.
Sure.
Alignment right. Then properties. Click on the properties. I want to know what is the calculated size for the PSV. Here.
Okay.
Calculated size and standard orifice size. Standard orifice size. Okay. Now let's talk about the outlet pipe, PSV outlet pipe. So this will be again 0.1 meter, 6-inch schedule 40.
6-inch.
Yeah, nominal size 6-inch.
6. Okay.
Schedule 40.
Okay.
Then finally the tank. So this tank represents the PSV outlet condition. So PSV outlet, what is the pressure? Okay, pressure model, you can keep it static pressure. Pressure model, static pressure. Right, and pressure will write 1 atmosphere is also 0 PSIG, but we'll use PSIG, so 0 PSIG. So that we will have some consistency with units.
Okay. Temperature.
Temperature will be calculated. Properties on flow sheet,
Okay.
again make it show. Show. Alignment right. And properties. So I would be interested in pressure and the temperature.
This properties. Okay.
And yes,
what?
so pressure is input and temperature is output result. So you can select temperature from result first.
Temperature.
Yeah, result temperature. Not
Oh,
everything, sir. Just select temperature. Expand result. Expand. Yeah. Uncheck. Just select temperature. Third list. Then you can expand input. Expand input. So there is pressure. Select pressure. Click OK. That's it. Click OK. All right. Please save your file. All right. Please, everybody tell me that you are completed till this. All right. Now it is 5:27. At 5:37 we'll be back. Let us continue. Everybody is here. Yes, Ajay, can you share your screen?
Okay.
As a temperature unit, you don't want to use degree C, right? So you need to change it to degree Fahrenheit. And then again, same thing. Right click.
Is that me?
Yes, Mr. Mark.
Okay.
All right. So you have given all the inputs. You can now click calculate, see what happens. No, sorry. We have not changed the fluid yet, right? So just click on the vessel. That is the tank. Vessel is down, right? You can see that fluid, it is still water. So,
okay.
So if I click on this, okay, so there is a huge list of different fluids, right? So if I go for, say, butane, yeah, if you go for butane, then it will be pure butane, right? If I go for propane, that will be pure propane. So there are some mix available, butane and propane, but those are not 50-50. Those have got some other combination, right? So we cannot use those, meaning we have to create our own mixture. So how to do that? We'll go to the database. So click on the fluids in database. So at the bottom, you can see there is new mix, add, delete. Click on new mix. New mix means new mixture. We'll call it as test C3, C4. No, C3, C4. C3 space C4.
Okay.
All right. Now you are in search bar. You can type butane. Butane.
Okay.
Then double click. Then type propane. Then double click. So I added two components, butane and propane. Okay. Now mixture type, it says mixture by weight, but we want mixture by mole.
Mole.
And what is the percent? 50, 50. All right, total is 100. Let others also complete this. Then we'll click OK.
Sorry. Yeah. What's happening?
Done?
It's hanging. The propane is not moving.
Propane is not moving.
I click OK and it's not working.
All right.
Surprise.
Just click here and here, then click OK. It should work.
I'm clicking. Okay. Maybe it's working now.
All right, then click again OK. Now you have created a mixture. Okay, 50-50 by mole. So you can now go to fluid and select this type T.
Yes.
Test C3, C4, click OK. Then we are done. You can click calculate, see what happens. Click on calculate.
Ajay sir, the mix is not getting activated.
Mix is not getting activated?
Yeah, we are not able to. If you click it also, it is not.
Can you share your screen, sir?
Yes.
Did you click on new mix?
No.
You need to create.
No, I made that new mix. Butane C3, C4, right? Test C3, C4.
Where is it?
I've done it. I've done it and then came here.
No, where is it? It should be there in the same list. No? So just type T.
No, it's not there. Test
Yeah,
C3,
it is there.
C4.
All right. So when you said C3 test C3, C4, you need to add in this only, right? So I'll just make it little bigger. All right. So we are here. And where is the mixture? I see what you have done. I'll just delete this. You clicked on add, sir. It should be new mix. So again type test C3, C4. Okay. All right. So this window should open. So here
Okay.
you can add the propane and butane.
Okay, that okay is missed.
Type propane. Then mixture by weight. It should be mixture by mole. 50-50. Now click OK. All right, again click OK. Mr. Mark, is it done?
Yeah. Yeah, I think so. I think it's done.
All right. You can click on that vessel, then change the fluid from water to test C3, C4.
This one.
Type T. Test. Yeah. Click OK. Now we can click calculate.
Okay.
All right. So temperature unit, you don't want to keep it degree C. So we will change it to degree Fahrenheit.
Yes.
Because it will be easy to compare what is the temperature drop.
Right.
So inlet is 167 temperature, outlet is 154. So that is understandable. And if you remember example 1, so we are also getting P orifice, right? So it is also giving same number. I checked in HYSYS the temperature drop. Okay, it is more or less matching. So we can trust this temperature out. So this was example 1, right? This was for critical flow, if you remember. Now for subcritical flow, we had some other input for outlet, PSV outlet, which was 55 psig. Remember example 2, 55 psig. So please change that input for the tank PSV outlet from 0 psig to 55 psig. And again run it. Calculate. Calculate.
I'm not able to see the calculate.
Really?
It's hidden. Okay.
I press that.
All right, so the P orifice will become now Q orifice, and the temperature from 167, the temperature drop will also be less because we are losing less pressure in this case.
Okay.
Yes.
In my case, it is still P orifice.
Did you click calculate?
Yes, sir.
Share
you calculate again. Press it again.
So let us take Mr. Mark advice. Click calculate. Okay, didn't work. Static pressure 50 psig. Actually, this was 55 psig, not 50. Then calculate. All right. So
Yes.
this works. So the conclusion is FluidFlow is it has gone one step ahead. This is now between hydraulic simulator and process simulator. See that? All right. So additional advantage to FluidFlow software. Any query on this? I'm sharing my screen. Now, if you see the folder which I shared with you, in that we have got this FluidFlow folder, right? So there is solved example from presentation, so that you already seen, and there is video and literature. Okay, so there are about 40 video files are there, short training videos are there. It's very good learning tool. Okay, please make use of that. And then there is one folder in that folder, that is FluidFlow Result Verification. This is 75 pages file, PDF file, right? It has got about 40 different problems. In next 2 weeks time, while your license is still valid, so I would request you to go through all these problems, okay, and try to solve it. Like in this example, you have got something with known flow. So flow, if you see, it is 500 APM. And then there is one pipe, 3-inch, 1000 feet length, and then outlet is connected to a tank. So once you model this, put the information, then once you run it, you should get more or less same results what FluidFlow has got, right? Then you need to compare that with the published data. If the difference between the published data and your results are not too great, meaning your simulation software is working just fine, then you can move to this some other example. Then you can go to little more complicated example, right? So that way, for all these modules, it has given several solved examples. So it is just a matter of time, how much time you can spend on learning the software, because more time you spend, better you become with the software. If you write this in your CV that you are expert in FluidFlow software, you will get better standing in the job market, especially those who are looking for a job at entry level. And if you write some articles, okay, if you solve some real project problem, like the one which you have seen earlier today for the Borel problem which I said. So there I have put only 3 exchangers. You can increase that to 30 or maybe 40. Write a paper that you can assume some numbers, right? And prepare a simulation report, and you do the simulation and then the results. So in LinkedIn, you can share this, and it is very good opportunity for you to market your skills. So this way you get noticed, right? And you get noticed for the good reasons. And if you're connected to the concerned person, relevant people in big consultancies, if they got any job opportunity, they will think about you, right? And that will be because I always say that getting a good job is actually a 6 months project. You need to first build your network on LinkedIn. You need to send connection requests to the concerned people, okay, not the piping engineer or not the junior level process engineers, but the HODs or senior manager, GM, okay, DGM level people. And once you have got connected with these people, you need to share something good, like VBA, this Excel file you can share. Okay, anything which is related to some technical stuff, you can share that. You need to take part in the discussion. In LinkedIn, somebody is asking any question, you Google it, okay, and then prepare your answer, and then put it there. It doesn't have to be your own answer, but studied answer. This way, people get a feeling that this guy, okay, he knows his stuff. So again, whenever there is any vacancy in their company, they will think about you, right? So this is not a like in a 1 week or 2 weeks time you will get famous, or your name will have some kind of value. It will take few months time at least, but it depends on how active you are on LinkedIn. And LinkedIn is very important tool these days. And whatever post you are doing on LinkedIn, please make sure that you tag me. I got something like 16,000 connections, right? So your post will get reach to 16,000 people. All right. So I don't mind if you tag me. I would actually encourage you to tag me, right? There is another folder here, FluidFlow Homework Anil. So this is one of you guys who has completed the homework which I had given after the FluidFlow, that free session I told, 3-hour session. So we don't usually give the certificate, participation certificate. We give expertise certificate. So once someone is called as expert, once that fellow has completed the homework, right? So FluidFlow, that 75 pages document, it has got 40 example files. You complete those 40, you get the certificate of expertise in FluidFlow. So simple deal. So same thing you can also do. These are the solved examples from those 75 pages document. I don't want you to just open it and see what has been done. The way you should use this folder is that you do it, you see what your answer is. If your answer is matching with the solved example, you don't have to look into these files. But you are getting huge difference, then that is when you can refer this file, right? Because if you first approach this, then you are not doing actually anything, right? Because looking at the problem, you will not be able to solve it. You have to do it yourself. Clear?
Yeah.
Okay, so this already you have got, it's available with you. All right, so Aspen Plus and FluidFlow, those were the two main topics for today. For Aspen Plus, I forgot to tell you one thing. The video what you have seen, the professor has given, recorded that video. It's not more than 15 minutes, right? And in 15 minutes video, she has made 2 or 3 mistakes, major mistakes, which she has corrected. So there is a big lesson. She could have deleted this video and put a new video without any mistake, right? She could have done that, but she didn't do it. Okay, this gives a very big, important lesson. In simulation, especially, you are allowed to make mistakes. Okay, as long as you correct it before the document goes to the client, right? And same is applicable in life also. You are allowed to make mistakes, but please make sure that you correct it in time.